From golden potato slices to crunchy corn cones and bold triangular tortilla chips, the making of Lay's chips, Bugles, and Doritos reveals the fascinating science behind some of the world's favorite snacks. Join us as we step inside modern factories to uncover the precision, machinery, and flavor engineering that transform simple ingredients into irresistible, crispy icons. The story begins with the potatoes themselves. Not every potato variety is suited for chip making. Factories rely on specific cultivars that are bred for high starch content, low sugar levels, and consistent size and shape. Too much sugar in a potato will cause chips to turn dark brown when fried, while irregular shapes make slicing inefficient. Farmers contracted to supply Lay's grow these varieties under strict guidelines. The potatoes are harvested, loaded into trucks, and delivered to processing plants within hours or days. Upon arrival at the factory, they are unloaded into massive receiving bays. Conveyor belts move the potatoes into storage silos, where they await inspection and cleaning. Before any potato is sliced, it undergoes a series of quality checks. Automated grading systems measure the size, weight, and surface condition of each potato. Those with defects, excessive bruising, or rot are rejected. Only the most uniform, healthy potatoes make it into the line. From here, the potatoes are washed thoroughly in large rotating drums filled with water jets that scrub away soil and debris. Dirt and stones are separated using flotation tanks or vibrating screens. After cleaning, the potatoes move toward the peeling station. Peeling is accomplished with either steam or abrasive methods. In steam peeling, potatoes pass through sealed chambers where high-pressure steam loosens the skins, which are then brushed off as the potatoes exit. In abrasive peeling, the potatoes tumble against rough rollers that scrape away the skin. Both methods remove the thin outer layer quickly and efficiently. Once peeled, the potatoes are rinsed again to remove loose skin fragments before being sliced. The slicing process is one of the most critical stages in chip production. High-speed rotating blades cut the potatoes into thin slices, often less than 2 millimeters thick. These slices can process thousands of pounds of potatoes per hour, ensuring uniformity in thickness so that every chip cooks evenly. Operators can adjust slice thickness depending on the variety being produced, whether standard Lay's, kettle-cooked versions, or specialty cuts like ridged chips. As soon as the slices are cut, they pass through streams of cold water to wash away excess starch, which prevents chips from sticking together during frying. From here, the potato slices travel to blanching. This step may surprise many consumers, but it is essential. Blanching involves briefly cooking the slices in hot water or steam, which removes residual sugars and further stabilizes starch content. This not only improves the color of the finished chip, but also helps achieve the crisp texture Lay's is known for. After blanching, the slices are dried using air blowers to remove excess moisture before entering the fryer. Frying is the heart of the operation. Long continuous fryers, sometimes stretching tens of feet, are filled with hot oil maintained at carefully controlled temperatures. The potato slices enter at one end and float through the oil on a conveyor system, cooking for just a few minutes. The timing must be perfect. Too short, and the chips will be soggy. Too long, and they will burn. During this time, water evaporates rapidly from the slices, leaving behind the crunchy structure of a finished chip. Oil is constantly filtered and refreshed to maintain quality, and temperature sensors ensure consistent frying conditions across the entire line. As the chips emerge from the fryer, they are immediately conveyed upward to drain excess oil. At this point, they are hot, crisp, and golden. The next step is seasoning. For classic Lay's, salt is sprinkled evenly across the chips using tumbling drums equipped with seasoning dispensers. For flavored varieties, seasoning powders made from dehydrated spices, flavor enhancers, and sometimes cheese powders or herbs are applied. The tumbling motion ensures every chip receives an even coating, which is key to delivering consistent flavor in every bite. Quality control is constant throughout the frying and seasoning process. Optical scanners and vision systems monitor chip color, shape, and size. Chips that are too dark, burnt, or misshapen are automatically blown off the conveyor with puffs of air. Human inspectors may also sample chips regularly, checking for texture and taste. Laboratory technicians analyze oil quality, salt levels, and seasoning distribution to ensure the final product meets strict specifications. Once seasoned, the chips head straight to packaging. Because chips are fragile, the packaging process must be both gentle and efficient. Multi-head weighers portion the chips into exact amounts for each bag. These machines use multiple small weigh bins to rapidly measure chips until the correct weight is reached, then release the portion into the packaging line. Vertical form-fill-seal machines shape rolls of printed film into bags, fill them with chips, and seal them shut. To protect the chips from breaking, a burst of nitrogen gas is added before sealing. This flushes out oxygen, preventing staleness, and inflates the bag slightly to act as a cushion during transport. The packaging lines run at astonishing speeds, filling hundreds of bags per minute. Sensors ensure each bag is properly sealed, and metal detectors scan for any potential contaminants. Finished bags are then grouped into cartons, which are stacked onto pallets by robotic arms. Pallets are shrink-wrapped and moved into climate-controlled warehouses awaiting distribution. The logistics of Lay's chips production are as carefully managed as the factory process. Chips must be transported quickly because freshness is central to the brand's reputation. Trucks equipped with climate control deliver the pallets to distribution centers, from which they are routed to supermarkets, convenience stores, vending machines, and restaurants. The supply chain is designed to minimize the time between frying the chip and the consumer opening the bag. Beyond the technical process, Lay's chips embody decades of refinement in snack manufacturing. The company has invested heavily in research and development, not only to create new flavors, but also to improve efficiency, sustainability, and consistency. Agricultural teams work directly with farmers to breed potato varieties suited for local climates and to implement practices that yield more uniform crops. Engineers continually refine slicing blades, fryers, and seasoning systems to reduce waste and improve control. Sustainability initiatives focus on recycling water, reducing energy usage in fryers, and optimizing packaging films to reduce environmental impact. The appeal of Lay's lies not only in its taste, but also in its engineering precision. The sound of a chip snapping between teeth, the lightness of its texture, and the balance of seasoning are all carefully engineered outcomes. A fraction of a millimeter in slice thickness, or a few seconds too long in the fryer, could change the entire eating experience. That is why every part of the process, from potato selection to packaging, is governed by data, automation, and skilled operators working together. When someone tears open a bag of Lay's and enjoys a handful of chips, they are tasting the culmination of hundreds of small steps. The soil where the potato was grown, the water sprays that washed it, the razor-sharp blades that sliced it, the hot oil that transformed it, the drum that seasoned it, and the nitrogen-filled bag that kept it crisp. All of these contribute to that simple, satisfying crunch. The scale of production is staggering, with factories capable of producing tens of thousands of pounds of chips per day, yet every chip is expected to taste the same as the one before it. The story of Lay's chips is therefore more than a story of snack food. It is the story of how modern food production combines agriculture, chemistry, engineering, and logistics to transform a humble potato into one of the most popular snack foods on Earth. It is a reminder that behind every seemingly simple product lies a world of complexity, innovation, and craftsmanship hidden in plain sight. The process begins with the main ingredient, corn. Bugles are made primarily from cornmeal, which provides the body and flavor of the snack. Cornmeal is produced by milling dried corn kernels into a fine powder, and only specific grades of corn are used to guarantee consistency. Large silos at the manufacturing plant hold tons of cornmeal, ready to be released in controlled amounts into mixing equipment. Alongside the cornmeal, other dry ingredients like wheat flour, salt, and sometimes a touch of sugar are blended in. These ingredients balance the flavor and contribute to the texture of the finished product. The first major transformation happens in the mixing stage. Industrial mixers combine the cornmeal blend with water and small amounts of oil, forming a dough. This dough has to be just right. Too wet, and it will not hold its shape. Too dry, and it will not expand properly in later stages. Operators rely on computerized systems to maintain exact ratios, and sensors inside the mixers constantly measure moisture content and temperature. Once the dough is prepared, it is fed into one of the most important pieces of equipment on the Bugles line, the extruder. Extrusion is where the magic of Bugles truly begins. An extruder is a powerful machine equipped with screws that push the dough through narrow openings under high pressure and temperature. As the dough moves through the barrel of the extruder, it is subjected to intense heat and shear forces. The heat cooks the starches in the cornmeal, gelatinizing them and creating a pliable, elastic material. At the end of the barrel, the dough is forced through specially designed dies. For Bugles, these dies are shaped to create the horn-like cone structure that makes the snack unique. When the hot dough emerges from the die, it undergoes rapid expansion as steam inside it escapes. This puffing action is what gives Bugles their hollow center and airy crunch. The shapes are cut to length immediately as they leave the extruder using rotating blades, ensuring uniformity. The newly formed Bugles are still soft and only partially cooked, so they must move quickly to the frying stage to achieve their final texture. Frying is central to the Bugles process. The extruded shapes are conveyed into long, continuous fryers filled with hot oil maintained at carefully controlled temperatures. Inside, the Bugles float and tumble as they fry for a set number of seconds. During this time, moisture is driven off rapidly, leaving behind a crisp, crunchy structure. The oil also contributes to the signature golden color and rich flavor of Bugles. Oil quality is constantly monitored. Filters remove food particles, and fresh oil is added regularly to maintain consistency. By the time the Bugles exit the fryer, they are fully cooked, crisp, and ready for seasoning. Seasoning gives Bugles their variety and appeal. Classic Bugles are lightly salted, but modern factories produce multiple flavors, from nacho cheese to ranch to caramel varieties. Seasoning is applied in large rotating drums, sometimes called flavor tumblers. As the Bugles move through these drums, finely powdered seasonings are dusted onto their surfaces. To help the seasoning stick, a fine mist of oil is often sprayed onto the Bugles just before the powders are added. The tumbling action ensures every cone gets evenly coated, and computerized dispensers control the exact amount of seasoning applied to avoid waste and maintain uniform flavor. Quality control is vital throughout the line. Cameras and optical scanners monitor the shape and color of the Bugles, instantly rejecting any that are misshapen, too dark, or broken. Samples are pulled regularly for sensory testing by technicians who check crunchiness, saltiness, and overall flavor. Laboratory equipment also measures fat content, moisture levels, and seasoning distribution to ensure the final product meets the company's strict standards. Once seasoned, Bugles are conveyed to the packaging area. Because they are light and fragile, Bugles require careful handling during this stage. Multi-head weighers portion out exact amounts of Bugles for each package. These machines use multiple small scales working in tandem, dropping bugles into collection buckets until the correct weight is reached. The portions are then dropped into form-fill-seal machines, where rolls of printed film are formed into bags. The bugles fall into the bag, and heat-sealing jaws close the top. To preserve freshness, nitrogen gas is flushed into each bag before sealing, pushing out oxygen and inflating the package slightly. This not only keeps the product crisp, but also cushions the bugles during shipping. Packaging machines run at incredible speeds, producing hundreds of bags per minute. Each bag is scanned to ensure proper sealing and correct weight. Metal detectors check for foreign materials, and vision systems verify the printing on the bags. Finished bags are then grouped into cases, stacked onto pallets by robotic arms, and wrapped for stability. From here, the pallets are moved to climate-controlled warehouses until distribution trucks carry them to retailers. The logistics chain is designed to move bugles quickly because, like all fried snacks, they are best when fresh. Trucks deliver them to supermarkets, convenience stores, and vending machines, where they await consumers eager to enjoy their crunch. The speed of this chain ensures that from the moment a corn kernel is milled to the time a bugle reaches a store shelf, only a few weeks may have passed. Bugles first appeared in the 1960s, created by General Mills, and they represented a new direction in snack foods. Unlike potato chips or simple corn chips, bugles require a unique extrusion process to achieve their shape and texture. Over the decades, the process has been refined and scaled up dramatically. Modern factories produce tons of bugles every day, yet the product remains consistent across batches. That consistency is the result of decades of engineering improvements, from more efficient extruder dies to better oil filtration systems and advanced seasoning technologies. Today, bugles are enjoyed around the world, with factories producing regional flavor variations to match local tastes. In some countries, sweet versions are more popular, while in others, savory cheese or spicy flavors dominate. Yet, the essential process, mixing cornmeal, extruding, frying, seasoning, and packaging, remains the same everywhere. The playful shape has also made bugles a nostalgic snack, as people often place them on their fingertips like edible claws, a habit that became part of the brand's identity. Behind that playful experience, however, lies a production line humming with activity. Massive silos holding tons of cornmeal, stainless steel extruders forcing dough through precision dies, fryers bubbling with oil, seasoning drums tumbling thousands of cones at once, and packaging machines wrapping hundreds of bags a minute. Every step is automated, synchronized, and monitored to ensure that the result is exactly what consumers expect: a light, crunchy, flavorful bugle. The production of bugles demonstrates how food engineering can transform simple raw ingredients into something extraordinary. By carefully controlling temperature, pressure, moisture, and timing, factories take powdered cornmeal and water and turn it into a snack with a unique shape, sound, and crunch. It is a process that balances art and science, tradition and technology, efficiency and playfulness. The end product may be small, but the effort that goes into every bugle is immense. So the next time someone opens a bag of bugles and slips one onto their fingertip before crunching it down, they are unknowingly participating in a story that stretches from farm fields of corn to high-tech factories filled with steel, heat, and automation. It is a story of how human ingenuity transformed a simple grain into a global snack, creating something both familiar and fun. The foundation of every Dorito is the corn tortilla, so the process begins with selecting the right kind of corn. Factories use specific varieties of yellow or white corn that have the correct balance of starch and protein for masa, which is the dough from which tortillas are made. The corn kernels arrive at the plant in bulk trucks and are emptied into storage silos that can hold hundreds of tons. Before use, the kernels are cleaned to remove debris, husks, and dust, From there, they move to the cooking and soaking stage, a process known as nixtamalization that dates back thousands of years to ancient Mesoamerican civilizations. In nixtamalization, corn is cooked in large stainless steel vats with water and food-grade lime, also known as calcium hydroxide. This step loosens the hulls of the kernels and changes the chemistry of the corn, unlocking flavor and improving nutritional value by making niacin more bioavailable. The cooked corn is then left to soak for several hours before being washed thoroughly to remove the loosened hulls. The result is nixtamalized corn, or hominy, which is now ready to be ground into masa. Grinding is performed using industrial stone grinders or steel mills that crush the soaked corn into a thick, pliable dough. This masa is the heart of Doritos production, and it has to be just the right consistency to roll and cut into tortillas. Too wet and the dough will stick. Too dry and it will crack during pressing. Operators continuously check moisture levels and adjust with water as needed. Once ready, the masa is fed into sheeting machines that press it into thin sheets, much like rolling out dough for a pie crust. These sheets pass under rotating cutters, shaped like triangles, stamping out the familiar Doritos shape. The excess dough is collected and recycled back into the sheeting system, ensuring no waste. At this point, the raw triangular chips are called masa chips, or tortilla chips, and they are not yet crunchy. They must be baked first to partially cook the dough and evaporate some of the moisture. The cut pieces are carried into long tunnel ovens, where hot air circulates around them for a few minutes. This baking step firms up the chips and prepares them for the critical frying stage. Frying is where Doritos achieve their signature crunch. The partially baked chips move along conveyors into continuous fryers filled with hot vegetable oil. The oil is maintained at precise temperatures to ensure that the chips cook evenly without burning. As the chips float and tumble in the oil, the remaining moisture rapidly evaporates, puffing up the structure and leaving behind a crisp, golden texture. The chips travel through the fryer for a set amount of seconds, then emerge glistening with oil. Immediately, they are lifted onto conveyors where excess oil drains away. Filtration systems continuously clean the oil, removing crumbs and replenishing it with fresh oil to maintain quality. Now that the chips are fully cooked, they are ready for seasoning, which is arguably the most defining feature of Doritos. Whether it is the classic nacho cheese, Cool Ranch, or one of the many limited edition flavors, the seasoning process is a delicate science. The chips enter large rotating drums, often called tumblers or flavor drums. Inside these drums, nozzles spray a fine mist of oil or seasoning slurry, while powdered flavorings are dusted evenly across the tumbling chips. The oil helps the powders adhere, and the tumbling ensures every triangle gets coated on both sides. The seasoning powders are carefully engineered blends of cheese powders, spices, salt, flavor enhancers, and sometimes sugar, depending on the variety. The balance must be perfect to deliver the intense, craveable taste Doritos are known for. Seasoning is monitored constantly by automated systems that weigh both chips and seasoning to maintain a consistent ratio. If too much seasoning is applied, the chips can become overpowering or messy. Too little, and they lose their signature punch. After seasoning, the chips are checked visually and by sensors for uniform coverage before moving to packaging. Packaging Doritos is an advanced, high-speed process designed to protect the fragile chips while keeping them fresh. Multi-head weighers portion out the chips into exact serving sizes, using multiple scales that combine small amounts until the correct weight is reached. The weighed portions are then dropped into form fill seal machines, where pre-printed film is formed into bags. As the chips drop in, the top of the bag is sealed with heat. Before sealing, nitrogen gas is flushed into the bag to displace oxygen. This step prevents the chips from going stale and also inflates the bag slightly, creating a cushion that protects the chips from breaking during shipping. Contrary to popular belief, the air in the bag is actually this protective nitrogen. The packaging machines operate at remarkable speeds, producing hundreds of bags per minute. Sensors verify that each bag is properly sealed, that the correct weight of chips is inside, and that the graphics on the bag are aligned. Defective bags are automatically rejected. The finished bags are collected, packed into cartons, and stacked onto pallets by robotic arms. Pallets are shrink-wrapped and stored in temperature-controlled warehouses before being shipped to distribution centers and eventually to retailers. Quality control is an invisible but critical part of the Doritos process. Every step is monitored by sophisticated systems, from moisture sensors in the masa to oil temperature probes in the fryers. Vision systems check chip shape and color, and random samples are pulled for taste tests by quality assurance teams. Metal detectors and X-ray scanners ensure that no foreign particles make it into the final product. Laboratories test seasoning powders for consistency in flavor and texture, while production supervisors track efficiency metrics to ensure the line runs smoothly. The global success of Doritos is not just due to their process, but also their adaptability. Factories around the world produce Doritos tailored to local tastes, using the same basic method but changing seasonings. In some regions, spicy varieties dominate, while in others sweeter or tangier flavors are preferred. Yet no matter the flavor, the crunch, triangle shape, and bold taste remain constant, reinforcing the brand identity. Doritos were first introduced in the 1960s, inspired by the traditional Mexican tortilla chip, but developed with a bold new approach, seasoning the chips heavily instead of leaving them plain. This innovation transformed a simple snack into a global phenomenon. Over time, the manufacturing process has been refined and scaled up to produce thousands of tons of Doritos per day across multiple continents. Today's factories combine ancient techniques like nixtamalization with cutting-edge automation, marrying tradition with technology in every chip. What makes Doritos particularly fascinating is the balance between fun and engineering. To the consumer, they are simply a flavorful snack. But behind the scenes, every detail is optimized. The angle of the cutter blades that produce the triangles, the airflow in the baking oven, the dwell time in the fryer, the particle size of the seasoning powder, and the gas composition in the bag. A Dorito is not just food. It is a product of precision science, designed to deliver an experience that feels spontaneous and indulgent, but is actually carefully controlled. So when someone rips open a bag of Doritos and is hit by the aroma of cheese or ranch seasoning, when they pick up a perfectly crisp triangle that delivers a satisfying crunch, they are experiencing the result of a complex journey, from the corn kernel to the masa dough, from the extruder cutters to the fryers, from the flavor drum to the nitrogen-flushed bag. Every step has been engineered to create a snack that is bold, fun, and dependable. Nutella's key ingredients are hazelnuts, sugar, palm oil, cocoa solids, skimmed milk powder, whey powder, lecithin as an emulsifier, and vanillin as a flavoring agent. Each of these ingredients is sourced globally, selected for consistency, taste, and availability. Hazelnuts, the signature ingredient, are predominantly sourced from Turkey, which produces more than 2/3 of the world's supply. However, Italy, Chile, and the United States also contribute to the global hazelnut harvest. Ferrero, the company behind Nutella, maintains long-term relationships with growers and has implemented traceability programs to ensure that hazelnuts meet quality standards for moisture content, size, and taste. Upon arrival at the processing facility, hazelnuts go through rigorous inspection and sorting procedures. This is a critical control point because the quality of the nut directly affects the flavor and texture of the final product. Optical sorters and vibrating sieves are used to remove debris, stones, and underdeveloped nuts. The selected hazelnuts are then subjected to a deshelling operation using mechanical crushers that crack the shells without damaging the kernels. These kernels are further inspected and cleaned before being sent to large-scale roasting units. Roasting is one of the most important flavor development stages in Nutella production. In industrial operations, continuous roasting ovens are used, where hazelnuts travel through a rotating drum or along a conveyor belt under a flow of hot air, typically between 140 to 160 degrees Celsius. Roasting duration and temperature are carefully controlled to bring out the nutty aroma and to reduce moisture to below 5%. After roasting, the nuts are cooled quickly to preserve their volatile aromatic compounds and prevent overcooking. The cooled hazelnuts are then transferred to grinding machines, where they are ground into a paste using roller mills and high-speed grinders. The result is a fine hazelnut paste with a smooth texture ready to be incorporated into the final mix. Meanwhile, other key ingredients are prepared in parallel. Sugar, which makes up a significant portion of the spread, is delivered in bulk as granulated white sugar. Before use, the sugar is pulverized in industrial fine grinders or pin mills until it becomes a powdered form with consistent particle size, often below 30 microns, to avoid any grittiness in the final texture. This powdered sugar is stored in silos and fed into the mixing tanks using pneumatic conveying systems. Cocoa solids, another essential ingredient, are typically received as cocoa powder. This powder undergoes sifting and magnetic separation to remove any foreign particles or metallic fragments. Skimmed milk powder and whey powder, both derived from dairy processing, are reconstituted into a slurry with water or added in dry form depending on the plant design. These milk-based ingredients contribute not only to flavor, but also to the creamy mouthfeel and protein content of the spread. Palm oil is selected for its semi-solid consistency at room temperature, which is ideal for producing a spreadable product that does not require refrigeration. Before blending, palm oil is filtered and heated to a controlled temperature to ensure uniform mixing. It is pumped into heated storage tanks, where it is kept in liquid form and circulated to prevent crystallization. Once all base ingredients are prepared, the process of mixing begins in large-scale stainless steel mixing tanks. These tanks are fitted with high-torque agitators and precision load cells that measure the exact quantity of each ingredient added. The powdered sugar, hazelnut paste, cocoa powder, milk powder, and palm oil are introduced sequentially, followed by small quantities of lecithin and vanillin. Lecithin acts as an emulsifier, allowing the fat-based palm oil to bind with the water-based milk components, ensuring the product remains stable and homogeneous. Vanillin, a synthetic or natural flavoring, gives Nutella its distinct sweet aroma. The mixture is subjected to a refining process to achieve the desired texture and particle size. This is often accomplished using 5-roll refiners or conching machines. The 5-roll refiner uses a series of precision-engineered steel rollers that progressively grind the mixture to a fine, uniform consistency, typically achieving particle sizes of around 20 microns. This stage is crucial for eliminating any detectable graininess, resulting in the smooth, velvety texture Nutella is known for. In some facilities, a conching step follows refining. In conching, the mixture is kneaded and aerated for several hours in large heated vessels. The process further develops flavor, reduces acidity, and allows volatile off flavors to evaporate. Temperature, shear force, and mixing speed are all tightly controlled to maintain product consistency. After conching, the mixture is cooled slowly to prevent separation and to stabilize the emulsion. Once the spread reaches the correct viscosity and temperature, it is pumped through sanitary pipelines to the filling stations. Filling lines are fully automated and consist of synchronized conveyor systems rotary fillers, and capping machines. The jars, made from glass or plastic, are cleaned with compressed air or ionized air blowers before being filled. Filling heads dispense the exact amount of Nutella into each jar with remarkable precision, ensuring minimal variation between units. Immediately after filling, jars pass through a sealing station where a foil membrane is applied to the mouth of the jar. This step is critical for maintaining freshness and preventing microbial contamination. The foil seal is typically induction sealed using a non-contact electromagnetic process that heats the foil and causes it to bond to the jar rim. Once sealed, the jars are capped with tamper-evident lids and conveyed to labeling machines. High-speed labelers apply brand-specific labels with information such as batch number, expiration date, and ingredients. Each jar then proceeds through a series of quality control checkpoints. These include weight checks, vision systems to verify correct sealing and labeling, and metal detection to ensure product safety. Defective units are automatically rejected and diverted for reprocessing or disposal. The entire packaging area is designed with hygiene in mind, using positive air pressure zones, clean-in-place systems, and stainless steel surfaces to reduce contamination risk. After packaging, Nutella jars are grouped into cartons or shrink-wrapped multi-packs, then stacked on pallets using robotic arms. Pallets are stretch-wrapped and labeled with barcodes for inventory tracking. From here, the product enters the distribution phase. Nutella's distribution logistics are a finely tuned operation. Pallets are stored temporarily in climate-controlled warehouses where temperature and humidity are maintained to prevent oil separation or spoilage. Inventory management systems track product movement using real-time data. Distribution centers coordinate with retailers, wholesalers, and export logistics to move products efficiently. Nutella is shipped in refrigerated or insulated containers only when necessary, though its high fat, low moisture content gives it considerable shelf stability. Throughout its supply chain, Nutella maintains compliance with international food safety standards such as ISO 22000, BRC, and HACCP protocols. Auditors regularly inspect facilities for compliance, and the entire process from hazelnut sourcing to jar sealing is documented for traceability and recall readiness. Automation, data collection, and machine learning are increasingly used to optimize processes, predict maintenance needs, and reduce waste. What makes Nutella's production so compelling is the precise synchronization of global sourcing, advanced food engineering, and automation technologies that allow for the consistent output of millions of jars per day. Every batch is a result of not just culinary science, but also the collaboration of agronomists, engineers, food technologists, and supply chain experts. Beyond the factory floor, Nutella's evolution continues with reformulations aimed at reducing sugar or incorporating more sustainable palm oil. Efforts to use recyclable packaging and implement blockchain for ingredient tracking reflect broader industry trends towards transparency and environmental responsibility. The foundation of Jif begins with its primary ingredient, peanuts. Specifically, the variety used in commercial peanut butter production is often the runner peanut, prized for its uniform kernel size, mild flavor, and high oil content. These peanuts are primarily grown in the southeastern United States, including states like Georgia, Alabama, and Florida, where sandy soils and warm climates create optimal growing conditions. Jif, owned by the J.M. Smucker Company, works closely with peanut growers through long-standing contracts to ensure consistent quality and supply. Before the peanuts even reach the factory, they're subjected to extensive grading systems operated by the USDA, evaluating factors like kernel size, moisture content, and damage from mold or pests. Once harvested, the raw peanuts are cured by drying them to a safe moisture level, usually around 10%. This drying stage is essential to prevent mold growth during transport. The peanuts are then shelled using mechanical shellers that crack the outer holes while leaving the kernels intact. After shelling, the peanuts are cleaned using air classifiers and vibrating screens to remove debris, dirt, and remaining shell fragments. These cleaned kernels are then transported in bulk to Jif's dedicated peanut butter production facilities, where their transformation truly begins. Upon arrival at the factory, peanuts undergo a second round of cleaning and quality control. Optical sorters equipped with high-speed cameras and sensors scan each peanut at astonishing rates, removing any discolored, damaged, or foreign material contaminated nuts. Metal detectors are also employed at this stage to ensure there are no traces of metal debris from harvesting equipment. These steps are critical not only for food safety, but also for maintaining Jif's smooth and consistent flavor. The next stage is roasting, arguably the most important phase for flavor development. Industrial peanut roasters are highly sophisticated machines capable of handling thousands of pounds of peanuts per hour. Jif uses a continuous dry roasting process where peanuts are evenly fed onto a perforated conveyor belt that moves through a tunnel of hot, forced air. Temperatures during roasting typically range between 160 and 180 degrees Celsius, with exact values finely tuned based on peanut size, oil content, and desired flavor profile. This process typically takes 15 to 30 minutes and is closely monitored using infrared sensors and real-time moisture analyzers. As peanuts roast, their proteins and sugars undergo Maillard browning, creating hundreds of volatile aroma compounds that contribute to peanut butter's distinctive roasted flavor. Immediately after roasting, the peanuts are rapidly cooled using chilled air blowers to stop the cooking process and lock in the developed flavors. This cooling also prevents oil separation and oxidation, both of which can negatively impact product shelf life. At this point, the roasted peanuts are ready to be ground, but first they must be blanched. Blanching in peanut butter production refers not to cooking in water, but to the mechanical removal of the thin, papery red skins that surround the kernels. In Jif's facilities, peanuts are sent through dry blanchers, machines that tumble the nuts at high speeds while heated air loosens the skins. Rotating brushes then remove the skins entirely, and high-capacity vacuum systems suck away the debris. The blanched peanuts are now a light golden color and are inspected one final time before grinding. The grinding stage is where peanuts are turned into a thick, luscious paste. Jif's production lines use a two-stage grinding process to achieve the brand's famously smooth consistency. First, peanuts are coarse ground using heavy-duty industrial grinders. These machines use stainless steel burrs or hammer mills to crush the nuts into a semi-solid mass known as peanut paste. This paste still contains some coarse particles and has not yet achieved its final texture. Next, the coarse paste is fed into ultra-high-speed fine grinders, often colloid mills, which apply extreme shear forces to reduce particle size down to 10 to 15 microns. This is a crucial target, as particle size below 20 microns ensures a mouthfeel that is perceived as completely smooth by consumers. During this stage, other ingredients are also introduced into the mixture. These include sugar, fully hydrogenated vegetable oils, salt, and sometimes molasses or mono and diglycerides. The oils, often made from rapeseed, cottonseed, or soybean, are used to stabilize the peanut butter and prevent oil separation on the shelf. Unlike palm oil or liquid vegetable oil, fully hydrogenated oils remain solid at room temperature and help give Jif its stable texture without requiring stirring. These additional ingredients are metered in with extraordinary precision using automated dosing systems connected to load cells and flow meters. Inline mixers ensure that each component is fully dispersed throughout the peanut paste. The temperature during grinding is carefully controlled, typically held between 60 and 75 degrees Celsius, to keep the product fluid without degrading flavor compounds. Once the peanut butter has been ground to the desired texture and all ingredients are thoroughly incorporated, it enters a holding tank under nitrogen blanketing. This protective gas layer prevents oxidation and helps preserve freshness during the short holding period before packaging. The product is then pumped to the filling lines through a network of heated sanitary stainless steel piping. Jif's packaging lines are models of efficiency and automation. Plastic jars, blow molded from PET or HDPE, are automatically unscrambled and conveyed into position. Before filling, jars pass through an air rinse station that uses ionized air to remove dust or plastic fragments. High-speed rotary piston fillers dispense precise volumes of peanut butter into each jar, minimizing air entrapment to avoid spoilage and maintain shelf life. Filled jars are then capped immediately using torque-controlled capping heads that screw on tamper-evident lids. After capping, jars pass through induction sealers where a foil membrane is bonded to the jar rim. This step uses electromagnetic energy to heat and seal the foil in milliseconds, creating a hermetic barrier that locks in flavor and protects against microbial contamination. The sealed jars move to labeling machines, where front and back labels are applied, followed by laser or inkjet printers that mark each jar with batch codes, production dates, and plant IDs. Throughout this packaging process, quality control is constant and rigorous. Automated vision systems inspect each jar for correct fill height, proper labeling, and cap placement. Metal detectors and X-ray scanners identify any contamination before product leaves the factory. Random samples are also pulled for texture analysis, oil separation testing, sensory panels, and microbiological screening. Any deviation from specifications leads to immediate corrective actions, and defective jars are removed from the line. Packaged jars are grouped into corrugated cardboard cases using robotic case packers. These cases are palletized by programmable robotic arms and stretch wrapped to ensure stability during transport. Each pallet receives a barcode label integrated into Jif's warehouse management system, allowing for real-time traceability from production to point of sale. Once palletized, the finished peanut butter is moved to distribution centers equipped with temperature and humidity control. Although Jif peanut butter is shelf-stable and does not require refrigeration, maintaining moderate temperatures during warehousing and shipping helps preserve flavor and prevent oil migration or texture degradation. From these central hubs, Jif is shipped to retailers, wholesalers, and export customers across the country and around the globe. The journey from raw peanut to finished jar is guided not only by mechanical precision, but also by a deep understanding of food chemistry, microbiology, logistics, and consumer expectations. Behind the familiar red-lidded jar is a network of engineers, food scientists, supply chain analysts, and production operators, all working in synchrony to ensure that every spoonful of Jif meets exacting standards. Advancements in automation and data analytics continue to refine the process. Modern Jif facilities are equipped with real-time monitoring systems, predictive maintenance software, and even machine learning algorithms that optimize roasting profiles based on moisture content and kernel density. Environmental controls ensure energy efficiency and waste reduction, and partnerships with peanut growers include sustainability initiatives aimed at soil conservation and water use reduction. The story of Hershey's syrup begins with its core ingredients: cocoa, sugar, water, corn syrup, salt, preservatives, and a few functional additives like potassium sorbate and xanthan gum. Each of these components is sourced with meticulous care to ensure consistency and food safety. Cocoa powder, the primary flavoring agent, is typically sourced from West Africa, where the Hershey Company partners with certified cooperatives to encourage sustainable farming practices. The cocoa beans are fermented dried, and shipped to the US, where they are roasted, ground, and pressed into cocoa cake. This cake is then pulverized into a fine cocoa powder, standardized for fat content, flavor profile, and color intensity. Upon arrival at Hershey's syrup production facilities, all ingredients undergo rigorous testing. The cocoa powder is checked for microbiological safety, color consistency, particle size, and moisture levels. Sugar, often in granulated form, is tested for crystal uniformity, purity, and absence of foreign materials. Corn syrup, used as both a sweetener and thickener, is delivered in tanker trucks and stored in heated silos. It is continuously circulated to prevent crystallization or microbial growth. Water used in the process is treated on-site, filtered, softened, and sanitized using UV light or reverse osmosis to ensure purity and microbial control. The first major production stage is blending the dry and liquid ingredients. The process typically starts with the creation of a sugar corn syrup slurry. In large stainless steel jacketed mixing tanks, granulated sugar is combined with warm water and corn syrup under controlled agitation. These tanks are equipped with variable speed mixers and internal temperature sensors to maintain optimal dissolution rates. The heating jackets help bring the mixture to a consistent temperature, usually between 55 and 70 degrees Celsius, to accelerate solubility while avoiding caramelization. Once a uniform syrup base is achieved, cocoa powder is added. However, dry cocoa is notoriously difficult to hydrate due to its high fat content and fine particle size, which cause it to float and form lumps when introduced to liquid. To overcome this, Hershey's production lines utilize high shear mixers and vacuum-powered powder feeders. The vacuum system pulls cocoa powder directly into the liquid stream, minimizing clumping and ensuring uniform dispersion. Simultaneously, high-speed rotor-stator mixers or inline homogenizers shear the mixture at thousands of RPMs, breaking down any agglomerates and producing a velvety, uniform chocolate syrup base. At this stage, salt and preservatives such as potassium sorbate are also introduced. These additions are precisely dosed using automated ingredient hoppers that weigh each component before releasing it into the blanders. Potassium sorbate acts as a mold and yeast inhibitor, extending the product's shelf life. Some formulations may also include citric acid or sodium citrate to adjust pH, which affects both microbial stability and flavor brightness. The syrup then enters the cooking phase. Unlike batch cooking in traditional kitchens, industrial syrup production uses continuous flow heating systems. The chocolate slurry is pumped through tubular or plate heat exchangers, where it is heated rapidly to pasteurization temperatures, typically between 85 and 95 degrees Celsius. This thermal treatment destroys any remaining microbial contaminants and activates the emulsifiers and stabilizers added in earlier steps. The product is held at this temperature for a specific dwell time as it flows through holding tubes, ensuring regulatory compliance with pasteurization standards. After cooking, the syrup must be cooled quickly to prevent overcooking and maintain the desired viscosity and flavor. This is achieved using chilled water heat exchangers, which rapidly bring the syrup down to below 30 degrees Celsius. Rapid cooling also helps stabilize the emulsion, locking in the texture and preventing ingredient separation. The cooled syrup is then transferred to intermediate holding tanks, where it is gently agitated and blanketed with nitrogen gas to minimize oxidation. At this point, the syrup undergoes several quality control checks. Samples are pulled and tested for viscosity using rotational viscometers, ensuring that the pourability matches the brand's standard profile. Colorimeters assess chocolate intensity and hue, while refractometers measure sugar concentration. In parallel, sensory panels may be employed to evaluate flavor, mouthfeel, and aroma. Microbial testing is conducted on every batch to confirm that pasteurization was effective and that no contamination has occurred. Once the product passes quality control, it is sent through final filtration before packaging. Fine mesh inline filters remove any particulate matter that may have formed during cooking or cooling. This ensures a perfectly smooth syrup with no grit or undissolved solids. Packaging Hershey's syrup involves a highly synchronized series of steps designed for both hygiene and speed. The most common containers are squeezable plastic bottles, which are blow molded from PET or HDPE on site or delivered pre-formed. These bottles are first conveyed through an air rinse system that blasts ionized air to remove dust or debris. They are then indexed into position beneath the filling nozzles. Filling is performed using servo-controlled, volumetric, or piston fillers. These machines are calibrated to deliver exact quantities of syrup, typically in the range of 650 to 800 grams per bottle, depending on size. The syrup is dispensed at controlled speeds to prevent splashing or air entrapment. No drip filling heads are often used to maintain clean bottle exteriors and reduce product waste. After filling, the bottles move to the capping station. Caps are sorted using centrifugal feeders and applied using torque-monitored capping heads, which ensure a tight seal without over-tightening. Each bottle is then passed under an induction sealer, where an aluminum foil seal is bonded to the bottle mouth using electromagnetic heating. This tamper-evident seal not only enhances shelf life, but also guarantees product integrity. Next, the bottles pass through a labeling machine where pressure-sensitive labels are applied with exacting precision. Labels include not just branding and nutrition information, but also critical traceability codes, including batch numbers, timestamps, and plant identifiers. These details are laser-etched or printed using inkjet coders. Before leaving the line, every bottle passes a series of automated inspection stations. Vision systems equipped with high-speed cameras check for correct fill levels, cap placement, seal integrity, and label alignment. Any non-conforming product is rejected and diverted to a separate inspection area for manual review. Approved bottles are grouped into cartons or shrink-wrapped multi-packs. Robotic case packers load the bottles into boxes, which are then sealed, labeled, and palletized. These pallets are stretch-wrapped and tagged with scannable barcodes for warehouse tracking. The entire process from filling to palletization is fully integrated into Hershey's manufacturing execution system, allowing for real-time monitoring and inventory control. Palletized syrup is transported to climate-controlled distribution centers. While Hershey's syrup is shelf-stable, temperature extremes can still impact viscosity and appearance. Warehouses maintain stable conditions to prevent thickening in cold weather or oil separation in high heat. From there, the product is dispatched to retail partners, online fulfillment centers, and export destinations. Throughout the supply chain, Hershey's implements strict food safety protocols, including compliance with the Global Food Safety Initiative, hazard analysis and critical control points, and FDA regulations. Traceability is maintained from raw cocoa bean to finished bottle, ensuring any issue can be traced and contained within hours. What makes Hershey's syrup so enduring in the marketplace isn't just its flavor, it's the precision and consistency made possible through modern food engineering. Every step of the process, from the aggressive mixing of cocoa powder to the final induction seal, is executed with scientific rigor. Equipment calibration, ingredient testing, and continuous improvement protocols ensure that each bottle tastes the same, pours the same, and satisfies the same cravings generation after generation. As the brand moves forward, sustainability is becoming an even greater focus. Efforts to reduce plastic use in packaging, improve energy efficiency in heating and cooling systems, and source more ethical cocoa are all part of Hershey's long-term production goals. Some lines are exploring bio-based pet alternatives for bottles and increasing recycling within plant operations. Continuous feedback from quality assurance teams and customer satisfaction metrics are used to refine processing parameters and optimize flavor retention across product shelf life. The process begins long before the chicken ever reaches the factory. KFC, like many large-scale food brands, maintains strict supply chain standards for its poultry. Birds are typically sourced from integrated poultry farms that meet the brand's animal welfare, health, and biosecurity requirements. These farms often operate under vertically integrated systems, meaning the entire life cycle of the chicken, from hatchery to grow out to processing, is managed within the same corporate ecosystem. This helps ensure uniformity in bird size, health status, and meat quality, which is critical when producing standardized menu items like spicy wings on an industrial scale. Once the chickens are ready for harvest, they are transported in temperature-controlled, sanitized trucks to centralized poultry processing plants. Here, the live birds go through a humane stunning and slaughtering process, typically involving controlled atmosphere stunning systems. This ensures both ethical handling and meat quality preservation. After slaughter, the birds are defeathered, eviscerated, washed, and cooled, typically through a cold water immersion chilling system that brings the internal temperature of the carcass down to safe levels as quickly as possible. The wings are separated during the portioning phase using high-speed automated cutting equipment. These machines use vision systems to identify and cut at precise anatomical joints, ensuring each wing is uniform in size and shape. This precision is crucial, not just for cooking consistency, but also for proper breeding adhesion and portion control in later steps. The selected wing portions, consisting of the drumette and flat sections, are then transferred to a dedicated wing processing line, where the transformation into spicy wings begins in earnest. Once the wings arrive at the spicy wing processing facility, the first stage involves a thorough inspection. Human inspectors and machine vision systems work in tandem to detect any physical abnormalities or foreign materials. Wings that pass inspection are then routed into a cold, tumbling drum, where they are lightly massaged with a saline-based pre-treatment solution. This helps the meat retain moisture throughout the cooking process and prepares the surface for better batter adhesion. At this stage, some facilities may also inject a phosphate or sodium-based marinade that helps improve juiciness and shelf life, although the exact formulation is proprietary and closely guarded by the brand. Following pre-treatment, the wings move down the line to the breading and seasoning stations, which are often the most visually engaging part of the process. First comes the wet batter application. Wings are submerged into a thin, flour-based slurry that acts as an adhesive layer for the dry coating. This slurry may contain modified starches, leavening agents, and a controlled pH buffer to ensure it sticks properly and reacts correctly during frying. After draining off excess batter, the wings are conveyed into the dry seasoning tumble. This dry breading stage is where the iconic spicy flavor is born. The seasoned flour blend used here is proprietary, but it typically includes a complex mixture of chili powders, paprika, black pepper, garlic powder, onion powder, and other flavoring agents, along with fine-grained flour and cornmeal for texture. A dusting conveyor or tumbling drum ensures even coverage on all sides of the wing. The machinery here is designed to prevent clumping and ensure that only an even, fine layer of breading adheres to each piece. In some facilities, a secondary pass through a flour press or compactor system ensures the breading is firmly embedded into the moist surface, giving it that distinctive crispy crunch once cooked. After seasoning, the wings are briefly set aside for a short dwell time. This resting phase, usually about a minute or two, allows the breading to properly adhere and partially hydrate. Next, they move into the pre-frying section of the line. This stage involves a high-capacity industrial fryer. often filled with high-stability vegetable oils, such as soybean or canola oil. The oil is heated to precisely controlled temperatures, typically around 350 degrees Fahrenheit, and the wings are flash fried for a brief period, just long enough to set the breading and create the initial crispy layer. This pre-frying step is not intended to fully cook the wings, but to lock in the structure of the coating so it maintains its texture during further processing. Once the pre-frying is complete, the wings are immediately conveyed to a blast chilling or par-fry cooling tunnel. This cooling step is critical for preserving the structural integrity of the coating and preventing carryover cooking that could degrade the texture. The temperature is rapidly reduced using forced cold air circulation, typically within a matter of minutes. Once cooled, the wings are either packaged for distribution to KFC outlets where final frying will occur, or they proceed to a fully cooked, frozen format, depending on the specific supply chain model used by the regional franchise. In systems where the wings are fully cooked at the central facility, they enter a final, high-temperature fryer that brings the internal temperature of the chicken to over 165 degrees Fahrenheit, ensuring it meets food safety standards. The duration and temperature profile of this final cook are tightly controlled and monitored by programmable logic controllers and sensor arrays that adjust heat levels in real time. The fully cooked wings then exit the fryer onto an inclined conveyor belt fitted with oil removal wipers or air knives to eliminate excess surface oil. Immediately following the cooking phase, the wings are transferred into a spiral or straight line blast freezer, depending on the plant layout. These freezers use ultra-cold air circulated at high velocity to freeze the wings down to storage temperatures of around -18 degrees Celsius. This rapid freezing process, known as individual quick freezing or IQF, prevents the formation of large ice crystals that could damage the structure of the breading and meat. The IQF process ensures that the wings retain their texture, flavor, and moisture when later reheated in KFC kitchens around the world. After freezing, the wings move into the packaging area. Here, automated systems weigh, portion, and package the wings into branded bags or cartons. Each package is checked for weight compliance using dynamic check weighers, and then sealed using high-speed heat sealers or vacuum packaging machines. Every package is labeled with traceability information, including batch codes, production time, and expiration dates, allowing for complete tracking through the supply chain. Quality control is deeply integrated into every step of this process, from metal detectors and X-ray machines that screen for physical contaminants to inline oil filtration systems that continuously purify frying oil to automated sensors that measure moisture content and temperature. Every phase of production is monitored by a combination of human oversight and real-time digital systems. Facilities that produce KFC spicy wings typically operate under globally recognized food safety standards such as HACCP and may also be certified under schemes like BRCGS or SQF. Once the wings are packaged, they enter the cold storage logistics chain. Pallets of frozen wings are loaded into refrigerated trucks that maintain a strict temperature range throughout transportation. These trucks deliver the product to regional distribution centers and eventually to individual KFC restaurants. In some regions, fresh, never frozen versions of the wings are delivered in chilled format and cooked to order in-store. In other areas, particularly where supply chains are longer or temperatures more variable, the IQF model is used to ensure quality is preserved until the point of sale. At the restaurant level, the final stage of the journey unfolds. Frozen or chilled wings are stored in temperature-controlled environments until needed. When ordered, the wings are deep fried one last time in high-capacity fryers, typically operating at around 350 degrees Fahrenheit. This final fry crisps the coating, rehydrates the spices, and brings the product to serving temperature. The result is a spicy, crispy, juicy wing that delivers the iconic KFC experience customers have come to expect. The process begins with the raw foundation of the product, the humble potato, but not just any potato will do. The ideal potato for Taco Bell nacho fries is typically a variety high in dry matter content, often russet Burbank or Shepherdie types, known for their low moisture, high starch, and robust structure. These characteristics ensure the fries achieve the perfect balance between a fluffy interior and crispy exterior after frying. These potatoes are sourced from large, vertically integrated farms primarily located in the Pacific Northwest of the United States or similar potato-producing regions around the world, where the climate and soil are optimal for consistent, large-scale yields. Harvesting is done using advanced mechanical harvesters that dig up the potatoes and gently lift them onto conveyor systems to avoid bruising. From there, they are transported to centralized washing and grading facilities where they are sorted by size, inspected for blemishes or defects, and washed thoroughly using high-pressure water jets and rotating brushes. Any potatoes that do not meet the factory standards are diverted to other uses such as dehydrated flakes or animal feed. Once approved, the potatoes are delivered in bulk to industrial fry manufacturing plants, where the transformation into nacho fries begins. At this stage, they are held in temperature and humidity-controlled storage rooms to preserve their starch content and prevent premature sprouting. When it's time to process, the potatoes are first sent through a series of peelers, usually steam peelers or abrasive roller systems, that efficiently remove the skins while minimizing product loss. This step is closely monitored using yield tracking sensors to ensure peeling efficiency and minimize waste. The peeled potatoes are then sliced using high-speed industrial cutting machines fitted with grid blades that create uniform fry shapes, typically thicker than traditional fast food fries to support the added seasoning and prevent oversaturation. These slicing systems are calibrated down to the millimeter to ensure each fry is cut to precise specifications, generally around 1 4-inch to 3 8-inch thickness. High-pressure water flumes carry the sliced fries through the line at speeds exceeding 20 feet per second, ensuring rapid, continuous processing. Next comes the blanching stage, where the sliced fries are briefly immersed in hot water, typically around 170 to 180 degrees Fahrenheit, for a few minutes. This partial cooking phase serves multiple purposes. It removes excess surface sugars that could cause uneven browning during frying, activates enzymes that improve texture, and begins the gelatinization of internal starches. After blanching, the fries are quickly cooled using chilled water or air blast tunnels to stop the cooking process and firm up the structure. Now partially cooked, the fries enter the par frying line. This is their first encounter with oil, and it's where the initial crispy layer begins to form. Large industrial fryers filled with high-stability oil, such as a blend of sunflower and canola oils, are heated to around 350 degrees Fahrenheit. The fries are submerged for a precise amount of time, usually less than 90 seconds, just long enough to form a protective crust on the outside. Sensors and computerized fry time controllers ensure that oil temperature remains consistent to prevent flavor degradation or uneven cooking. Immediately after par frying, the fries pass through a de-oiling conveyor, where vibrating belts and air knives remove excess surface oil. The fries are then conveyed into a seasoning chamber, which is one of the most distinctive stages in the production process. Here, Taco Bell's proprietary spice blend is applied. The exact recipe is tightly controlled, but it's known to include ingredients like paprika, garlic powder, onion powder, chili powder, and finely milled salt, combined with natural flavor enhancers and color stabilizers. A continuous tumbling drum with angled paddles ensures every fry is evenly coated, while fine misting sprays may be used to lightly dampen the fries and help the powder adhere without making the product soggy. Once seasoned, the fries are flash frozen using a high-velocity IQF freezer system. In this stage, powerful cold air, chilled to minus 40 degrees Fahrenheit or below, is blasted across the fries in a spiral or linear tunnel. This rapid freezing process locks in flavor, moisture, and structure, preventing ice crystals from damaging the surface coating. The IQF method ensures that each fry remains separate and doesn't clump, which is critical for later portioning in restaurant operations. After freezing, the fries are transferred to the packaging line. Automated systems weigh and fill bulk fry containers or food service size bags, which are then sealed using heat sealing equipment. Each bag is printed with a batch code, production date, and temperature tracking markers. Metal detectors and X-ray machines scan each package to ensure no foreign materials are present, a key component of food safety compliance. Packaged fries are loaded onto pallets and stored in deep freeze warehouses until they are ready for distribution. The nacho cheese sauce, an essential companion to the fries, has its own equally rigorous production process. The base of the sauce is typically a processed cheese blend made from cheddar, milk proteins, and emulsifying salts like sodium citrate or sodium phosphate. These ingredients are carefully combined in industrial kettles equipped with steam-jacketed heating systems and high-shear mixing paddles. Stabilizers, such as modified starches and gums, may be added to ensure the sauce maintains a smooth, pourable texture even after cooling and reheating. Once the cheese base is prepared, spices are added, typically a blend of jalapeno flavoring, chili extract, and other proprietary ingredients that give the nacho sauce its signature kick. The mixture is emulsified under vacuum to remove air bubbles and then pasteurized using a continuous flow heat exchanger. This process heats the sauce to over 165 degrees Fahrenheit for a controlled amount of time to destroy microbial contaminants while preserving flavor and color. After pasteurization, the cheese sauce is hot-filled into sterilized pouches or cups under aseptic conditions. These containers are then sealed and either cooled through a water cascade system or sent into spiral chillers. The sealed containers are packed into cartons and labeled for refrigerated or shelf-stable distribution, depending on the formulation used for the region's supply chain. With both the fries and the cheese sauce packaged and preserved, the products are transported through a cold chain logistics network. Fries are shipped frozen in insulated trucks to regional distribution centers and then delivered to Taco Bell restaurants in freezer-safe cartons. The cheese sauce, often refrigerated, follows a separate cold storage route. Each location has specific temperature monitoring systems in place to ensure food safety compliance throughout transit and storage. At the restaurant level, the frozen fries are stored in walk-in freezers until needed. When an order comes in, the fries are portioned out and deep fried in vegetable oil, using high-efficiency commercial fryers. This final fry is where the crispy golden texture is fully developed. The temperature is maintained at a consistent 350 degrees Fahrenheit, and the fry time is usually between 2 and 3 minutes. Once cooked, the fries are immediately drained, then served hot in Taco Bell branded packaging. The cheese sauce is reheated either in a hot holding unit or using a hot water bath system that brings it to serving temperature without burning. The sauce must reach at least 140 degrees Fahrenheit to meet food safety and quality requirements. Once heated, the sauce is portioned into small dipping containers or drizzled directly over the fries in some menu variants. Throughout the entire industrial journey of nacho fries, rigorous quality assurance and food safety protocols are in place. Samples from each batch are taken at various stages and tested for microbiological contaminants, seasoning distribution, oil content, moisture levels, and cooking performance. Facilities operate under strict guidelines such as FDA, FSMA requirements, or international standards like ISO 22000 and HACCP. Every element of production, from the slicing of potatoes to the pasteurization of cheese sauce, is documented and auditable to ensure full traceability. The process begins with the heart of the Whopper, the beef patty. Burger King has long differentiated its burgers by using a flame-grilled method, but before the grill comes into play, the patty must first be produced. Beef is sourced from large-scale, certified suppliers that adhere to strict animal welfare, traceability, and sustainability standards. These suppliers operate integrated meat processing facilities where cattle are harvested and broken down into primal and subprimal cuts under USDA or equivalent oversight. The beef used for Whoppers is typically derived from a mix of chuck, round, and sirloin cuts, blended to achieve a desired fat content, often around 20%, for optimal juiciness and grill performance. Once the meat is ground, it is passed through an emulsifying system that ensures even distribution of fat and protein. This step helps prevent gristle pockets and improves the patty's binding structure. The ground beef mixture is then conveyed to high-speed patty-forming machines that press and extrude the meat into uniform rounds using a die plate and compression mold. These industrial formers operate at speeds of hundreds of patties per minute and are capable of adjusting thickness and diameter to exact specifications, typically around a quarter-pound raw weight for each Whopper patty. The formed patties are placed on a conveyor belt and flash frozen using cryogenic tunnel freezers or spiral IQF systems that use liquid nitrogen or carbon dioxide to rapidly bring the internal temperature below -18 degrees Celsius. This ensures that each patty retains its cellular structure and juiciness upon cooking. Once frozen, the patties are transferred to automated packaging lines, where they are stacked in moisture barrier cartons or vacuum-sealed pouches, labeled with production dates, and passed through metal detectors before being palletized for frozen storage and global distribution. Equally important to the Whopper is the bun, a sesame seed-topped, split bread roll that undergoes its own industrial journey. Buns are produced at high-capacity commercial bakeries where production lines can generate tens of thousands of units per hour. The dough is made from a blend of wheat flour, water, sugar, yeast, and vegetable oil, along with dough conditioners and preservatives to maintain softness and shelf life. The mixing phase involves large-scale planetary or spiral mixers that knead the dough to the correct gluten development. After mixing, the dough enters a resting phase in fermentation-proofing chambers where it rises under controlled temperature and humidity. The dough is then portioned by volumetric dividers and shaped into balls by automated rounders. These pre-shaped dough pieces are loaded onto proofing trays and undergo a final rise before baking. The tops are lightly misted with water or egg wash and sprinkled with white sesame seeds by mechanical applicators. The buns are baked in continuous tunnel ovens that stretch over 100 feet in length and operate at temperatures exceeding 400 degrees Fahrenheit. Once baked, they pass through a rapid cooling system using ambient or chilled forced air to bring their temperature down before slicing. Each bun is sliced horizontally by high-speed rotary blades and inspected for consistency. To maintain freshness, buns are either packaged in modified atmosphere packaging or frozen shortly after cooling and then bagged in polyethylene liners. They are coated with traceability information and packed into corrugated cartons for delivery to regional warehouses and restaurants. The vegetables, lettuce, tomatoes, and onions are sourced from contracted agricultural operations that follow strict GAP protocols. Iceberg lettuce, preferred for its crunch, is harvested using semi-automated field machines that cut and core the heads in one motion. The lettuce is then transported in refrigerated trucks to processing facilities where it is washed in sanitized flumes, dried using centrifugal systems, and shredded using stainless steel cutting blades designed to preserve crispness without bruising the leaves. Tomatoes are selected for firmness and uniform diameter to ensure neat slices. They are cleaned using high-pressure spray washers and sliced using rotary slicers fitted with adjustable blades. The sliced tomatoes are layered into stackable trays or nested compartments to prevent crushing during transit. Similarly, onions are peeled mechanically using high-pressure air systems, sliced into rings, and packaged under chilled conditions to retain freshness. The pickles, another key flavor component, are made from cucumbers processed in bulk brining tanks. After harvest, cucumbers are washed, sorted by size, and submerged in a vinegar-based brine seasoned with salt and spices. After fermentation or quick pickling, depending on the formulation, they are sliced into consistent chips using high-speed slicers and packaged in oxygen barrier pouches or buckets for food service use. Condiments for the Whopper, primarily mayonnaise and ketchup, are manufactured in specialized condiment production facilities. Mayonnaise production begins with the emulsification of oil, egg yolk, vinegar, and stabilizers in high-shear mixing tanks equipped with homogenizers. The emulsion is pasteurized through a plate heat exchanger to eliminate pathogens while preserving viscosity and color. Ketchup is cooked in steam-jacketed kettles and blended with tomato concentrate, sugar, vinegar, and a proprietary spice mix. Both condiments are filled into sterile plastic pouches, bag-and-box systems, or pump-compatible canisters for use in restaurant dispensers. Cheese slices used in variants like the Whopper with cheese are produced from processed cheese blends that ensure meltability and consistency. These are extruded into sheets, cut into slices, and layered with separators to prevent sticking. The slices are then vacuum packed or nitrogen flushed for refrigerated storage and distribution. With all components produced and shipped to Burger King locations, the final assembly of the Whopper occurs in the restaurant, but the process is built upon a strict operational framework. Each location stores the beef patties in a walk-in freezer and thaws them under refrigerated conditions. When an order is placed, the patty is cooked on Burger King's signature broiler, a chain-driven flame grill system that uses open gas flames to charbroil the beef as it passes through on a conveyor. This broiler, unique to Burger King, is a marvel of fast food engineering. The system allows for consistent flame contact, resulting in seared grill marks and a characteristic smoky flavor. Sensors monitor patty temperature and broiler speed to ensure the patty is fully cooked to a safe internal temperature of 160 degrees Fahrenheit without overcooking. The cooked patties are briefly held in warming trays under precise time constraints to maintain texture and temperature. Meanwhile, the buns are toasted in a dedicated bun toaster, which uses radiant heat or infrared technology to give the interior a light crispness while leaving the exterior soft. The assembly station is laid out for ergonomic speed and accuracy. A Whopper bun base is placed on a wrapping sheet or clamshell box. The bottom bun receives a layer of mayonnaise, followed by shredded lettuce, 2 to 3 tomato slices, and the flame-grilled patty. Next come the ketchup, sliced onions, pickle chips, and finally the top bun. Employees are trained to follow a specific build order and ingredient placement protocol to maintain consistency across all locations. Once assembled, the Whopper is either wrapped or boxed using pre-printed branded materials and placed into warming cabinets for immediate delivery to the customer or drive-through window. Food safety, quality assurance, and traceability are enforced at every step of the Whopper's life cycle. Raw materials are tracked via digital systems that log harvest dates, batch codes, and production facilities. Burger King suppliers and franchises are subject to regular third-party audits, temperature verification, and microbiological sampling. Any deviation from standard operating procedures, whether it be in patty cook temperature, bun freshness, or condiment integrity, triggers corrective action protocols. It all begins with the raw materials. For Kellogg's cornflakes, the primary ingredient is whole grain yellow corn, chosen for its high starch content, consistent kernel size, and clean flavor profile. The corn is sourced from farms that meet strict quality standards, often grown in regions where soil conditions, temperature, and moisture levels yield the optimal crop. The grain suppliers must pass multiple certification checks to ensure there are no contaminants, pesticides above allowed thresholds, or off-spec kernels. Alongside the corn, other ingredients such as sugar, malt flavoring, and a precise blend of vitamins and minerals are procured from certified ingredient suppliers. Even minor ingredients undergo laboratory testing for purity and safety before they are ever allowed into the production flow. When the corn arrives at the Kellogg's plant, it is unloaded from bulk transport trucks or rail cars into massive silos. These silos are fitted with aeration systems to keep the grain dry and prevent mold growth. Before storage, the corn passes through a preliminary cleaning system. This includes vibrating screens to remove large debris, aspirators that blow away dust and light particles, and magnetic separators to capture any stray metallic fragments. The cleaned corn is then weighed using automated bulk scales, ensuring precise tracking of raw material usage for both production planning and regulatory compliance. From storage, the corn moves towards the first processing step, cooking. But before cooking, the kernels need conditioning. This involves sending them through a pre-wet process in which they are steamed lightly or soaked in warm water to raise their internal moisture content to the right level for even cooking. Moisture meters along the line continuously monitor this process. Once conditioned, the kernels are conveyed to large pressure cookers, sometimes referred to as steam cookers or rotary pressure vessels. These massive stainless steel cylinders rotate slowly while injecting steam and adding a carefully measured solution of sugar, malt flavor, and salt. The steam not only cooks the kernels, but also helps the added flavors penetrate evenly into each piece of corn. The cooking process gelatinizes the starch inside the kernels, making them ready for the next transformation. After cooking, the hot, softened kernels need to be cooled and partially dried. They exit the cooker onto a series of vibrating cooling conveyors where ambient or slightly chilled air is blown across them. This stops the cooking process, stabilizes the texture, and prepares them for the critical flaking stage. However, the corn is still too moist to be flaked properly. It first enters large industrial dryers, often drum style or fluidized bed dryers, which reduce the moisture content to an exact level that will allow the flakes to shatter cleanly, rather than smear or tear during rolling. The drying process is closely monitored by moisture probes and computer-controlled exhaust systems to maintain uniformity. The next stop is tempering. Tempering involves holding the cooked, dried kernels in large bins for several hours so the remaining moisture distributes evenly throughout each kernel. This equalization is key to creating flakes that cook evenly in the final toasting step. The bins are equipped with gentle agitators or slow conveyors to prevent clumping and to keep airflow steady. Once tempered, the kernels are ready for the flaking process. Here, they pass through massive flaking mills. Each mill consists of two large, precision-ground steel rollers, often cooled internally to prevent heat buildup. These rollers press each kernel flat in a single pass, creating the familiar, thin, oval shape. The gap between rollers is set to a fraction of a millimeter and is adjusted automatically to ensure all flakes have the same thickness. The flaking mill is one of the most critical pieces of equipment because the thickness of the flake determines not only the texture, but also the way it will toast and absorb milk later on. Freshly flaked corn is still pale and slightly soft, so it moves immediately into the toasting ovens. These ovens are long, multi-zone conveyors where hot air, often at temperatures over 300 degrees Fahrenheit, flows over and through the flakes. The first zones drive off remaining moisture, while the later zones caramelize the sugars and develop the golden brown color. The toasting stage is where the signature crunch develops as the starch matrix hardens. The aroma at this point is unmistakable. Warm, slightly sweet, and distinctly cereal-like. Automated sensors monitor the color and moisture level, and adjustments to air temperature or conveyor speed can be made in real time to maintain consistency. Once toasted, the flakes are cooled on open conveyor belts with filtered ambient air. Rapid cooling helps lock in crispness and prevents condensation inside the packaging later. At this stage, the cereal may pass under a vitamin and mineral application system. In some Kellogg cereals, a fine mist or powder of fortified nutrients is sprayed or dusted onto the flakes, then gently tumbled to ensure uniform coating. The application rate is measured to fractions of a gram to comply with nutritional labeling requirements. From here, the flakes head toward the packaging. Before they can be boxed, the cereal is screened to remove overly small particles or broken flakes. These screenings may be collected for use in other products or as livestock feed. The main product stream passes through a final quality check, which can include metal detectors, optical sorters, and even X-ray scanners to detect any foreign matter. Samples are pulled at regular intervals and sent to an on-site lab, where technicians test for moisture content, color, flavor, and texture to ensure the batch meets Kellogg specifications. The packaging line is a marvel of precision. The cooled cereal is metered into form-fill seal machines or pre-made bag fillers. In the classic box format, an inner bag made of food-grade plastic film is formed from a continuous roll filled with an exact weight of cereal using high-speed scales, then heat-sealed. The filled bag is automatically inserted into a printed cardboard carton, which is glued shut and stamped with a production code for traceability. Packaging machines operate in perfect synchronization with the upstream production flow to prevent overfill, underfill, or product jams. Sealed boxes travel down conveyors to be bundled into shipping cases. Robotic case packers arrange multiple boxes into corrugated cardboard cases, which are sealed and labeled with both barcodes and batch codes. These cases are stacked by robotic palletizers into tall, stable loads, often wrapped with stretch film to secure them for transport. From the moment the corn arrived at the plant, the environment has been strictly controlled for food safety. Air is filtered, surfaces are sanitized regularly, and all equipment is cleaned in place using automated cleaning systems that circulate hot water and food-safe detergents through the machinery. Employees follow stringent hygiene protocols, including wearing protective clothing, hairnets, and gloves. Every step in the process is documented for traceability, so that in the rare event of an issue, the source can be identified and contained quickly. Once the pallets of finished cereal leave the plant, they are loaded into clean, dry trucks or shipping containers. Distribution centers receive the pallets, store them under controlled conditions to prevent moisture pickup or crushing, and coordinate shipments to retailers. Retail stock rotation ensures that consumers always get cereal at peak freshness. The shelf life of cornflakes is typically several months when stored in a cool, dry place, thanks to the low moisture content and protective packaging. Beyond the basic process, Kellogg's has invested in continuous improvement and technological innovation in its plants. Automation now allows for real-time monitoring of every parameter, from the temperature inside the toasting oven to the precise thickness of flakes coming off the mill. Data analytics can flag trends before they become defects, enabling preventive adjustments. Energy efficiency measures such as heat recovery from ovens and optimized air handling systems have been integrated into many plants to reduce environmental impact. Cheerios production begins long before the famous little toasted oat rings take shape on the factory line. It starts with selecting the right oats because in a product like Cheerios, where oats are the star ingredient, the raw material defines the flavor, texture, and nutritional profile. The oats are sourced from farms that grow specific varieties of whole grain oats prized for their uniform kernel size, high beta-glucan content, and consistent milling performance. These farms are often located in cooler climates where oats thrive, and the crops are harvested, cleaned, and transported in bulk to the manufacturing plant under strict quality control conditions. When oats arrive at the facility, they are unloaded into massive storage silos equipped with aeration systems to maintain dryness and prevent spoilage. Before being accepted into the main storage bins, the oats pass through mechanical cleaning systems. These systems remove dust, small stones, and plant debris using vibrating screens, air aspiration units, and magnetic separators that capture any trace of metal contamination. Every incoming lot of oats is also tested in the plant's quality control lab for moisture content, protein level, microbial safety, and the absence of unwanted residues. The next step is oat milling. In the Cheerios process, oats must be transformed from raw groats into a workable form for extrusion. This begins with dehulling, which removes the outer husk from each oat kernel. The cleaned oats are fed into impactor hullers, where centrifugal force cracks the hulls without damaging the inner groats. The hulls are separated from the groats using aspiration and gravity tables, and the groats proceed to a kiln for heat stabilization. Heat stabilization is a controlled toasting step in which the groats are gently heated to deactivate enzymes that can cause rancidity. This step also enhances the nutty flavor of the oats. From there, the groats are rolled or ground into oat flour. For Cheerios, a blend of whole oat flour and sometimes additional grain flours like cornstarch or wheat starch is used to create the right dough properties for extrusion. The oat flour is measured precisely, and minor ingredients such as sugar, salt, and a vitamin-mineral premix are prepared in separate dosing hoppers. All these dry ingredients are fed into a pre-mixing system, where they are blended into a uniform mix before moving to the wet mixing stage. Wet mixing takes place in an industrial preconditioner or mixer, where water and sometimes steam are added to the dry mix. This creates a damp, pliable dough. The ratio of water to dry mix is carefully controlled because it determines how the dough will behave in the extruder. Sensors inside the mixer continuously measure dough temperature, moisture, and homogeneity. This hydrated dough is conveyed immediately into the heart of the Cheerios process, the extrusion system. Cheerios are made using a rotary die extruder. The dough is fed into the extruder barrel, where rotating screws knead and compress it under controlled heat and pressure. The barrel is divided into zones, each with a specific temperature and mechanical shear setting. As the dough moves forward, the heat and pressure partially cook the starches and gelatinize them, creating a texture that will puff slightly when released from the die. At the end of the barrel, the dough is forced through a die plate that has hundreds of tiny, ring-shaped openings. Each opening has a small pin in the center, creating the hole of the Cheerio as the dough extrudes around it. As the dough emerges from the die, it is cut to size by high-speed rotating knives mounted just outside the plate. The freshly cut rings are soft, warm, and slightly expanded. These rings now enter the drying and toasting stages. First comes the primary drying conveyor, where warm air is blown over the pieces to reduce moisture and prevent sticking. After this initial drying, the Cheerios are transferred to large, continuous toasting ovens. These ovens operate with multiple temperature zones. In the early zones, moisture is driven off steadily, and in the later zones, higher heat creates the light brown toasted color and enhances the flavor through Maillard reactions. The toasting step is critical for the signature crunch of Cheerios. Moisture sensors and color cameras monitor the product as it travels through the oven, and computer-controlled adjustments are made on the fly to keep the output consistent. After toasting, the Cheerios must be cooled before packaging. They move along cooling conveyors where filtered ambient air is circulated. The goal is to bring the product to a stable temperature, so condensation will not form inside the packaging. This also allows the texture to set fully. In some varieties, a light coating of sugar syrup or flavoring may be applied at this stage using a rotating drum or tumbler. But for classic plain Cheerios, no additional coating is added after toasting. Next, the cooled cereal is sifted to remove small fragments or broken rings, which are collected for use in other applications or for animal feed. The main product stream passes through a final quality control system that includes metal detection, weight checks, and sometimes optical sorting to ensure that every piece is intact and meets size specifications. Samples are pulled for sensory evaluation, which includes tasting for flavor, checking crunch, and verifying that the shape and color meet the brand standard. Packaging begins with precise weighing. Multi-head weighers dispense exact amounts of cereal into form-fill-seal bagging machines. In the classic box format, an inner bag is formed from a roll of plastic film, sealed at one end, filled with cereal, and then heat sealed at the top. Automated arms place the sealed bags into pre-printed cardboard cartons. Each carton is glued shut and stamped with a lot code that contains information about the date, time, and line of production for traceability. These cartons travel along conveyors to case packers, where machines arrange them into corrugated shipping cases. The cases are sealed, labeled, and then stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during shipping. Finished pallets are stored temporarily in a distribution warehouse with temperature and humidity controls to preserve product freshness. From the distribution center, the pallets are loaded into clean, dry transport trucks and shipped to retailers nationwide. Retail stock rotation ensures that older product is sold first, keeping Cheerios at their optimal freshness for consumers. The shelf life of Cheerios is generally several months due to their low moisture content and protective packaging, but quality is highest in the weeks immediately after production. Throughout the entire process, food safety and quality assurance are paramount. The factory environment is designed for easy cleaning and sanitization with enclosed systems that protect the product from airborne contamination. Employees follow strict hygiene protocols, including wearing hairnets, gloves, and uniforms, and undergoing regular training in food safety practices. Many parts of the plant operate under hazard analysis and critical control points plans, ensuring that every stage, from raw grain to finished package, is monitored for safety risks. Cheerios production is also heavily automated, with control systems tracking hundreds of variables in real time. Data on dough moisture, extrusion pressure, oven temperatures, and packaging line speeds is logged continuously. This allows operators to detect subtle deviations and correct them before they impact the final product. Over the years, the efficiency and precision of Cheerios manufacturing have improved dramatically through advances in automation, ingredient handling systems, and real-time quality monitoring. The making of Frosted Flakes begins with one key ingredient: corn, but not just any corn will do. The factories that produce Frosted Flakes work with carefully selected varieties of yellow dent corn that have the right starch composition, kernel size, and moisture profile to create large, uniform flakes with a crisp bite. These corn varieties are grown in regions where climate and soil conditions produce consistent, high-quality harvests. Before a single load of corn is accepted, it must pass rigorous inspections for moisture content, kernel integrity, absence of mold or mycotoxins, and overall cleanliness. This ensures that, from the very start, the product's signature taste and texture are protected. The corn arrives at the plant in bulk trucks or rail cars and is unloaded into massive storage silos. These silos are fitted with aeration systems that keep the grain cool and dry to prevent spoilage. Before the corn can be stored, it is cleaned using a series of mechanical processes. Vibrating screens remove large debris, aspirators blow away dust and lightweight particles. and magnets capture any stray bits of metal that may have entered during harvesting or transport. After cleaning, the corn is weighed using bulk scales, allowing the plant to track exactly how much raw material will be processed into frosted flakes. Once the corn is ready for production, it is first conditioned. Conditioning involves soaking or steaming the kernels to bring their internal moisture to an optimal level for cooking. This step softens the kernels and helps them absorb flavors more evenly later in the process. The conditioned corn is then fed into massive rotary pressure cookers. In these cookers, the kernels are tumbled slowly while being injected with live steam under pressure. A syrup blend of sugar, malt flavor, and a pinch of salt is added, infusing the corn with a sweet, malty taste that will deepen during toasting. This cooking stage gelatinizes the starch inside the kernels, transforming them from hard grain into a tender, flavor-packed base. When the cooking cycle is complete, the hot softened corn is discharged onto cooling conveyors where fans blow ambient or slightly cooled air over the kernels. This halts the cooking process and stabilizes their texture. At this point, the kernels still contain too much moisture to be flaked properly. They move into large industrial dryers, either drum-style or fluidized bed designs, that gradually remove water until the kernels reach the precise moisture level needed for flaking. The drying process is tightly controlled because too much drying will cause the flakes to crumble, while too little will cause them to smear or tear during rolling. After drying, the corn undergoes tempering. This step involves holding the kernels in large bins for several hours to allow the remaining moisture to distribute evenly throughout each kernel. Tempering ensures uniform flaking and helps prevent uneven toasting later. Gentle agitators or slow-moving conveyors in the bins keep the kernels from clumping together while promoting even airflow. Now comes one of the most important steps in the frosted flakes process: flaking. The tempered kernels are fed into massive flaking mills where pairs of enormous, precision-ground steel rollers press each kernel flat in a single pass. The rollers are often water-cooled internally to prevent heat buildup, which could cause sticking or premature cooking. The gap between rollers is adjusted with extreme precision to produce flakes of consistent thickness. This thickness is critical. It determines how the flakes will toast, how they will break in the mouth, and how long they will stay crisp in milk. Freshly flaked corn is pale, soft, and flexible, so it immediately enters long toasting ovens. These are continuous conveyor ovens with multiple heating zones. In the early zones, hot air drives off remaining moisture, locking in the flake's shape. In the later zones, higher heat brings out the golden brown color, deepens the flavor, and crisps the texture. The toasting stage is also when much of the sweet, roasted aroma is developed. Sensors throughout the oven monitor moisture levels and color, and adjustments to temperature and conveyor speed can be made instantly to keep every batch consistent. Once the flakes are perfectly toasted, they are cooled on open-air conveyor belts to stabilize their structure. This cooling step also prepares them for the next stage that gives frosted flakes their name: sugar coating. The cooled flakes enter large rotating tumblers known as coating drums. Here, a warm sugar syrup is sprayed onto the flakes in a fine mist. The syrup is made from refined sugar dissolved in water and heated to the right viscosity so it coats evenly without soaking the flakes. As the flakes tumble, every surface becomes covered in a thin, glossy layer. The amount of syrup applied is carefully measured to achieve the brand's signature sweetness without overpowering the cereal's natural corn flavor. After coating, the flakes pass through another drying system, often a warm air tunnel, which removes excess moisture from the syrup and crystallizes the sugar onto the flakes' surfaces. This creates the sparkling, crunchy coating that stays intact until the cereal is submerged in milk. The drying time and temperature are crucial. Too short and the sugar will be sticky. Too long and it may over-caramelize. Following coating and drying, The cereal undergoes final quality checks. It is sifted to remove broken flakes and small sugar granules. The main product stream passes through metal detectors and sometimes X-ray scanners to ensure there are no foreign materials. Samples are pulled regularly for moisture testing, color analysis, sweetness measurement, and texture evaluation. Taste panels may also evaluate random samples to confirm flavor consistency. The finished frosted flakes are then ready for packaging. The cooled flakes are conveyed to multi-head weighing machines that dispense exact portions into high-speed packaging lines. For the classic box format, an inner bag is formed from a continuous roll of food-grade plastic film, sealed at the bottom, filled with cereal, and then heat-sealed at the top. The sealed bag is automatically inserted into a pre-printed cardboard carton. The carton is glued shut, stamped with a production code for traceability, and checked by sensors to ensure it is properly sealed. From here, the cartons are conveyed to case packing machines, where they are grouped into corrugated shipping cases. These cases are sealed with adhesive tape or hot glue, labeled with batch information, and stacked onto pallets by robotic palletizers. The pallets are wrapped in stretch film for stability during transit and stored in a climate-controlled warehouse until they are shipped. Every step of the frosted flakes process takes place in a facility designed with strict food safety controls. Air handling systems keep dust and contaminants out of production zones, while stainless steel surfaces are regularly cleaned and sanitized. Automated clean-in-place systems wash the interior of cookers, dryers, and coating drums without dismantling the equipment. Workers wear protective clothing, hairnets, and gloves, and they follow hygiene protocols to prevent contamination. Once the product leaves the factory, it travels to distribution centers, then to retailers. Stock rotation at the store level ensures that consumers get fresh product with the sugar coating intact and the flakes as crisp as they were on the day they were made. Proper storage, cool, dry, and away from direct sunlight, keeps frosted flakes in peak condition for months. Behind every box of frosted flakes is a tightly controlled sequence of thermal, mechanical, and chemical transformations. From the high-pressure steam cooking that gelatinizes the starch, to the precise flaking that creates the perfect surface for sugar adhesion, to the final toasting that seals in crunch and flavor, every step is engineered for consistency. This is why a bowl of frosted flakes tastes the same, whether it was made in Michigan, Canada, or halfway across the world. The history of nerds stretches back to the early 1980s, when they were first introduced to the market as a playful, intensely flavored treat unlike anything else in the candy aisle. The appeal lay in their irregular shapes, their bright colors, and their signature combination of sweet and sour notes. Behind the scenes, however, the magic is created not by whimsy, but by a carefully controlled industrial process. It all begins with the sourcing of raw ingredients. The foundation of nerds is refined cane or beet sugar, which arrives at the factory in bulk deliveries, often in multi-ton silos or in large paper sacks that are emptied into storage hoppers. This sugar is highly refined to ensure purity, with a moisture content so low that it will not clump during storage or handling. Alongside the sugar come shipments of corn syrup, which acts as a binding and texturing agent, as well as citric acid and malic acid to provide the tartness that defines Nerd's flavor profile. The plant also receives concentrated flavor oils and powdered colors approved for food use. Each batch of these ingredients is tested in a quality control laboratory before it enters the production stream, ensuring compliance with both flavor and safety standards. The production of Nerds begins with a core, which is essentially a tiny granule of sugar that serves as the seed for the candy's build-up process. These seed crystals are often derived from slightly coarser sugar grains that have been screened to a uniform size. The real artistry begins in the heart of the coating pans, large rotating drums that are the beating heart of sugar candy manufacturing. Inside these stainless steel pans, the sugar seed crystals are gently tumbled as a fine mist of sugar syrup is sprayed over them. This syrup is prepared in a heated mixing tank, where granulated sugar is dissolved into water under controlled temperature, often in the range of 110 to 130 degrees Celsius, and then blended with a precise amount of corn syrup to control crystallization. The hot syrup flows through jacketed piping to prevent premature cooling before being atomized into a fine spray within the coating pan. As the syrup coats the tumbling seed crystals, it begins to harden upon contact with the cooler air inside the pan, forming a thin outer layer. Then, a light dusting of dry sugar is sometimes added to further build the surface and maintain separation between individual granules. This cycle repeats dozens or even hundreds of times, each layer adding microns of thickness to the growing candy piece. Operators closely monitor airflow, humidity, and drum rotation speed to ensure that the candies do not stick together or form unwanted lumps. During this stage, the irregular shapes that make nerds so distinctive begin to emerge. Unlike machine-molded candies that have identical geometry, these sugar-coating pans produce slight variations in size and contour, which means every nerd has its own unique outline. The gradual layering process continues until the candy reaches the target size, which is typically just a few millimeters in diameter. Once the base size is achieved, flavoring and coloring are introduced. This is a delicate operation, as liquid flavors and colorants must be distributed evenly without dissolving the sugar surface. The pan operator reduces airflow slightly and sprays a concentrated solution of flavor oils, acids, and color onto the candy bed. In many cases, flavors are applied in small incremental sprays with pauses for tumbling in between, allowing the surface to dry and preventing color streaking. The flavors are carefully balanced so that the acids provide tang without overwhelming the sweetness, creating the signature taste that fans recognize instantly. After flavoring and coloring, the candies undergo a polishing step. This involves applying a thin layer of glazing agent, such as carnauba wax, which gives the nerds their characteristic sheen and helps protect them from moisture pickup during storage. The glaze is applied in a separate polishing pan, where candies are tumbled with a small amount of the molten wax until every piece has a uniform shine. At this point, the candies are allowed to cool and set fully, ensuring that their coatings have hardened completely. Cooling may occur in ambient air or in a temperature-controlled chamber that maintains low humidity to prevent stickiness. The fully cooled candies are then transferred via gentle vibratory conveyors to the packaging area. The packaging operation for nerds is an impressive example of precision weighing and high-speed filling. Because the candy pieces are so small and irregular, multi-head weighers are commonly used to ensure accurate portioning. These machines use multiple load cells arranged in a circular pattern, dropping small amounts of candy from each channel until the combined total matches the target weight. This system minimizes giveaway and ensures that each box contains exactly the promised amount. The iconic Nerds boxes are constructed from food-grade cardboard with an inner lining that protects against moisture. The packaging line begins by folding and gluing the flat-printed cartons into their box shape, often with automated carton erectors that can handle hundreds of units per minute. The weighers then deposit the precise quantity of candy into each box through stainless steel chutes. For dual flavor boxes, a partition is inserted inside the carton, and two separate weighing heads feed different candies into each side simultaneously. Once filled, the boxes pass through a closing station, where flaps are folded and glued shut, followed by a coding station that prints lot numbers and best before dates for traceability. The sealed boxes are then collated into larger trays or shrink-wrapped bundles for ease of handling in distribution. Quality control continues all the way through the process. In addition to the raw ingredient checks at the start, samples of candy are pulled from the line at regular intervals to assess flavor consistency, color uniformity, and physical integrity. The hardness of the coating is measured with specialized instruments, and the acidity levels are checked to ensure the sourness remains within the brand's signature profile. Metal detectors are integrated into the conveyor system to ensure no foreign materials make their way into the final product. From the packaging area, the candies move to the warehouse for distribution. Since Nerds are low in moisture and have a hard sugar shell, they are relatively stable during storage. However, they are kept in a cool, dry environment to maintain their texture and prevent color fading. Pallets of finished product are wrapped and staged for shipment to wholesalers, retailers, and export markets around the world. The journey from sugar seed to the vibrant, tangy pellets in your hand is a testament to how much engineering is hidden inside even the simplest candies. Each step, from syrup spraying in massive tumbling pans to the delicate flavor infusion and high-speed filling lines, is executed with precision to deliver the playful, crunchy experience that has kept Nerds popular for decades. Over time, manufacturing technology for Nerds has evolved to improve efficiency and consistency. Early production relied heavily on skilled operators adjusting pans by sight and sound. Today, advanced automation systems track humidity, airflow, and syrup application rates with sensors and feedback loops, ensuring that every batch meets exacting standards. The result is a product that remains faithful to its original flavor and texture while benefiting from modern advancements in food processing equipment. There is also increasing focus on sustainability in candy production. Many factories now recover and reuse heat from syrup cooking kettles, implement water-saving cleaning systems for coating pans, and work with suppliers to source sugar from more sustainable agricultural operations. Packaging too is being reevaluated, with lighter materials and improved recyclability being considered for the future. What makes the production of Nerds especially fascinating is the balance between art and science. The process is rooted in classical confectionery techniques that date back centuries, yet it is executed on a scale and with a precision that only modern machinery can achieve. The slight variations in size and shape that give Nerds their charm are not flaws, but deliberate results of the panning process, embraced as part of their identity. The story of Twizzlers begins long before the candy reaches the factory floor. As with many mass-produced confections, the foundation is in the sourcing of high-quality raw materials. The primary ingredient is refined wheat flour, which gives Twizzlers their chewy, slightly bread-like texture. This flour arrives at the plant in bulk tanker trucks and is stored in towering silos that protect it from moisture and contaminants. From here, it is gravity-fed or pneumatically conveyed through sealed pipes to the mixing area. Alongside flour, the recipe calls for corn syrup, which provides sweetness, binding power, and flexibility, as well as sugar, which boosts flavor and adds structure. Vegetable oil, often in the form of soybean or palm oil, contributes to the mouthfeel, while food-grade colors and flavorings give Twizzlers their signature appearance and taste. Every ingredient undergoes rigorous inspection in the quality control laboratory before it can be released to production. Flour samples are checked for protein content and moisture levels. Sugar is screened for crystal uniformity, and corn syrup is tested for viscosity and purity. Liquid flavors and colors are reviewed for consistency against reference standards. Once approved, ingredients move into the blending stage, where the transformation from raw material to candy dough begins. The mixing process takes place in large stainless steel horizontal mixers fitted with heavy-duty paddles or spiral blades. The operation starts with a precise ratio of flour and sugar being combined, followed by the gradual addition of corn syrup and water. These mixers operate under controlled speeds to ensure the dough develops evenly without excessive heat buildup. Oil is incorporated next, coating the flour particles and contributing to the dough's smooth, pliable consistency. Throughout mixing, operators monitor temperature and dough texture, making small adjustments to moisture content if necessary. In many plants, this step is partially automated, with sensors tracking torque resistance in the mixer to determine when the dough has reached the ideal elasticity. Once mixed, the candy dough is transferred to the extrusion line. This is the stage where Twizzlers take on their famous twisted rope form. The dough is fed into a large extruder, essentially a high-powered screw press that forces the material through a specially designed die. The screw inside the extruder rotates at a controlled speed, kneading and pushing the dough forward while maintaining an even temperature to prevent premature setting. At the end of the barrel, the die features multiple openings shaped to produce the exact cross-section of a Twizzler rope. For the classic variety, the die includes ridged channels that create the candy's spiral grooves. As the dough emerges from the die, it is still warm and soft, making it easy to shape but vulnerable to deformation. To preserve the precise geometry, the extruded ropes immediately enter a cooling conveyor, a long belt that passes through a tunnel where chilled, dehumidified air circulates. This step lowers the candy's temperature and sets the outer surface while maintaining a chewy interior. The speed of the conveyor is carefully calibrated so that cooling is uniform along the rope's entire length. An interesting detail of Twizzlers' production is that the twist in each rope is not solely a result of the die design. The conveyor belt itself may be equipped with rollers that gently rotate the ropes as they move forward, enhancing the spiral effect. The amount of twist is a delicate balance. Too much rotation can weaken the structure and cause breakage, while too little results in a less distinctive look. After cooling, the ropes are ready to be cut to size. Cutting is performed by high-speed guillotine blades or rotary knives synchronized with the conveyor movement to avoid crushing the candy. For standard snack-sized Twizzlers, lengths are typically between 6 and 8 inches, but the same line can be adjusted to produce miniature bites or extra long versions. The cut pieces now move towards the packaging area, but before they are boxed or bagged, they undergo inspection. Quality control technicians pull samples from the line to check twist uniformity, diameter, weight, and surface texture. The moisture content is measured to ensure the candy retains its chewiness during storage. Flavor is also evaluated by trained sensory panels who compare each batch to established taste profiles. Packaging Twizzlers is a study in efficiency. Depending on the product format, they may be wrapped in flexible plastic film, placed in cardboard trays, or sealed in resealable pouches. The packaging machinery begins with an in-feed system that gently aligns the ropes into uniform stacks. These stacks are then transferred into forming tubes where the plastic film is drawn around them, sealed along the edge with heat, and cut into individual packs. Heat-sealed jaws close the ends to lock in freshness and protect the candy from moisture and oxygen. Lot codes, manufacturing dates, and product identifiers are printed directly onto the packaging by inkjet or thermal printers, ensuring traceability for every unit. Sealed packages are collected onto a takeaway conveyor and then collated into larger cartons for shipping. These cartons are stacked on pallets by robotic palletizers, which arrange the boxes in stable patterns and wrap them in stretch film to secure the load. From here, the pallets are moved to the warehouse, a temperature-controlled environment designed to maintain product quality. Although Twizzlers are relatively stable due to their low moisture and high sugar content, excessive heat can cause surface stickiness or deformation, so storage temperatures are carefully regulated. The finished products are then shipped to distribution centers, retail outlets, and export markets. Behind all of this is a network of automation systems and process controls that keep production running smoothly. Modern Twizzlers plants rely on programmable logic controllers to coordinate mixer cycles, extrusion pressures, conveyor speeds, and packaging rates. These systems integrate with quality control data, enabling operators to adjust parameters in real time if a batch shows signs of deviation from the standard. The flavoring of Twizzlers deserves special mention. While the classic strawberry variety is the most famous, the process allows for a wide range of flavors, from cherry to chocolate to licorice. In each case, the flavor oils are blended into the dough at the mixing stage to ensure even distribution. The choice of flavor affects other parameters as well. For example, chocolate varieties may require a slightly different extrusion temperature due to the fat content in cocoa powder, while licorice varieties may use molasses or anise oil that alter dough handling characteristics. Over the years, Twizzlers production has been refined not only for efficiency, but also for consistency. Early methods required more manual handling, with operators guiding ropes off the extruder and cutting them by hand. Today's operations are highly automated, with minimal direct contact between workers and the product. This not only improves hygiene, but also allows for higher output with fewer defects. Sustainability is becoming a greater focus in candy manufacturing as well. Plants are investing in closed-loop water systems for cooling conveyors, energy-efficient ovens for any heat treatment steps, and waste reduction programs that recycle off-spec candy back into the mix when feasible. Packaging materials are also being evaluated for recyclability, with thinner films and plant-based plastics under consideration. What makes the Twizzlers process so fascinating is the combination of bakery-like dough handling with candy-making sweetness. The extrusion technology is similar to that used in pasta production, yet the ingredients and post-extrusion handling are firmly rooted in confectionery science. It is a hybrid process that demands both mechanical precision and an understanding of how sugars, starches, and fats interact under heat and pressure. When you pick up a pack of Twizzlers, you are holding the result of careful ingredient selection, finely tuned mixing and extrusion, precise cooling and twisting, and airtight packaging. Each rope is the product of countless micro adjustments in speed, temperature, and formulation that ensure the candy's texture, flavor, and appearance are exactly as consumers expect. The story of a Haribo gummy begins with the ingredients, each of which is selected for quality and consistency. At the heart of the recipe is gelatin, a protein derived from collagen that gives the candy its characteristic elastic texture. This gelatin arrives at the factory in dry, granulated form and must be carefully hydrated before use. Alongside gelatin, the formulation includes glucose syrup, often produced from wheat or cornstarch, which provides body, prevents crystallization, and contributes to the chewiness. Sugar is another mainstay, giving sweetness and structural integrity. Additional ingredients include citric acid for tartness, natural and artificial flavorings for each variety, and food-safe colorants to create the rainbow of hues that define Haribo's product line. Every batch of ingredients undergoes rigorous testing in a quality control laboratory before it reaches the main production floor. Gelatin is checked for bloom strength, which determines the firmness of the finished candy. Glucose syrup is tested for solids content and viscosity, ensuring it will flow and set properly in the cooking process. Flavor and color concentrates are measured for potency and compared against established standards. Only when the raw materials pass inspection are they released to the production team. The first major step in making Haribo gummies is the cooking process. This begins in large stainless steel vessels called dissolvers or cooking kettles. Here, sugar, glucose syrup, and water are combined and heated under controlled conditions. The heating process brings the mixture to a high temperature, often in the range of 110 to 140 degrees Celsius, allowing the sugars to dissolve completely and the syrup to thicken. Once the sugar syrup reaches the correct density, pre-soaked gelatin is added. The gelatin is never boiled, as high temperatures would damage its gelling properties. Instead, it is stirred in gently once the syrup has cooled to a safe range, typically between 80 and 90 degrees Celsius. At this point, flavorings, acids, and colors are added. For gummy bears, this might include lemon, orange, raspberry, apple, and strawberry flavor profiles, each paired with a corresponding color. The additives are metered in with precision pumps to ensure every batch is consistent in both taste and appearance. Stirring must be thorough but gentle to avoid incorporating excess air bubbles, which could mar the candy's surface. Once the mixture is fully blended, it is ready to be formed into shapes. This is where Haribo's distinctive starch molding process comes into play. The company uses a method called the Mogul system, an automated production line that allows liquid candy to be deposited into detailed molds with incredible precision. The process begins with large trays filled with a fine, dry cornstarch powder. This starch serves two purposes. It prevents the sticky candy from clinging to the trays, and it helps wick away excess moisture during the setting stage. Each tray passes through a stamping unit where metal dies press the shape of the candy into the starch. Tiny, bare outlines, cola bottle profiles, or whatever form is being produced. The impressions are crisp and exact, ready to receive the warm, liquid mixture. From the cooking kettles, the candy syrup is pumped through heated pipelines to a series of depositor nozzles. These nozzles align perfectly with the starch impressions and release measured amounts of syrup into each cavity. The depositor can switch flavors and colors quickly, allowing for multiple varieties to be produced on the same line with minimal downtime. Once deposited, the trays of liquid candy are conveyed into a long climate-controlled curing room. Here, they rest for 12 to 72 hours, depending on the recipe, temperature, and humidity. During this time, the gelatin network fully sets, giving the candy its final chewy texture, while the starch continues to absorb surface moisture. The curing rooms are kept at specific humidity levels to prevent the candies from drying out too much or becoming sticky. When curing is complete, the trays move to the demolding stage. The gummy shapes are gently lifted from the starch, which is recovered, dried, and sieved for reuse in future molding. Any excess starch clinging to the candies is removed through a combination of mechanical shaking and soft air jets. The gummies, now fully formed, have a matte appearance and a slightly tacky feel at this stage. To give them the glossy finish consumers recognize, the candies are transferred to large rotating drums called glazing pans. Inside, they are tumbled with a thin coating of food-grade waxes such as carnauba or beeswax, along with oils that enhance shine and prevent sticking. The glazing process is quick but crucial, as it also provides a protective barrier against moisture changes during storage. With their appearance perfected, the gummies proceed to the packaging area. Here, high-speed conveyors feed them into multi-head weighers, machines equipped with multiple hoppers that dispense exact amounts to achieve the target package weight. The candies are dropped into pre-formed bags or into the forming tubes of vertical form-fill-seal machines. These machines create a bag from a continuous roll of printed film. Seal the bottom, fill it with the candy, then seal the top in one continuous motion. For variety packs, sophisticated sorting systems group different gummy shapes and flavors in precise ratios before they reach the weighing step. This ensures that every bag contains the intended assortment. Packaging films are chosen for their barrier properties, keeping the gummies fresh while displaying bright branding. Each bag receives a lot code and best before date for traceability, then passes through metal detection equipment as a final safety measure. The finished bags are gathered into cartons, stacked onto pallets, and wrapped in stretch film to stabilize them for shipping. Pallets are moved to temperature-controlled storage areas until they are loaded onto trucks bound for distribution centers and retailers around the world. Throughout the entire process, quality control remains a constant presence. Samples from each batch are taken at multiple points. from syrup cooking to molding, curing, and packaging, to ensure that every aspect meets Haribo's specifications. Technicians test texture with penetrometers to confirm the perfect chew, measure pH to monitor acidity, and use colorimeters to verify hue accuracy. Flavor panels taste test samples to ensure the product matches established sensory profiles. The production of Haribo gummies has evolved significantly over the decades. Early batches were made by hand in small copper kettles and poured into starch molds one tray at a time. Today's lines can produce hundreds of thousands of pieces per hour, with computerized systems controlling every variable. Yet the core principles remain the same: quality ingredients, precise cooking, careful molding, and patient curing. There is also a growing emphasis on sustainability within Haribo's operations. Many plants now use energy recovery systems to capture heat from cooking processes, recycle starch indefinitely, and source gelatin and sugar from more sustainable supply chains. Efforts to reduce packaging weight and increase recyclability are also underway, ensuring that the joy of gummy bears has a smaller environmental footprint. What makes Haribo's process fascinating is the blend of old-world confectionery craftsmanship and high-tech automation. The mogul molding system, for instance, is an industry standard, yet it still relies on principles that candy makers have used for over a century. The long curing time is a reminder that some aspects of candy making simply cannot be rushed if the desired texture is to be achieved. By the time a bag of Haribo gummies reaches the shelf, it has undergone a transformation from raw sugar, syrup, and gelatin into a perfectly shaped, flavorful, and brightly colored treat. Behind each piece is a network of ingredient sourcing, controlled cooking, precision molding, and patient curing, all supported by layers of quality control and packaging expertise. The production of sunflower oil in modern industrial facilities is a meticulously orchestrated process that transforms raw sunflower seeds into the clear, golden oil commonly used in cooking and food production. This journey begins with the careful selection and preparation of sunflower seeds, ensuring that only the highest quality seeds are processed to produce premium oil. Upon arrival at the processing plant, sunflower seeds are subjected to a rigorous cleaning regimen designed to remove a variety of impurities that may have been introduced during harvesting and transportation. This initial phase is critical, as foreign materials such as soil, stones, plant debris, and metal fragments can compromise the efficiency of the extraction process and the quality of the final product. The cleaning process typically involves several stages, each employing specialized equipment tailored to eliminate specific types of contaminants. The first line of defense in the cleaning operation is the magnetic separator. This device utilizes powerful magnets to attract and remove ferrous metal particles from the stream of sunflower seeds. Metal contaminants can originate from various sources, including harvesting equipment and transport containers, and their removal is essential to prevent damage to downstream processing machinery and to ensure product safety. The seeds pass over or through magnetic plates or drums, where metallic impurities are captured and separated from the bulk material. Following magnetic separation, the seeds proceed to vibrating sieves or screens. These machines consist of perforated plates or mesh screens that oscillate at high frequencies, effectively sorting the seeds based on size and shape. Larger impurities, such as sticks, leaves, and oversized debris, are unable to pass through the screen openings and are thus separated from the smaller, uniform sunflower seeds. The vibration intensity and screen aperture sizes are carefully calibrated to optimize the removal of unwanted materials, while minimizing the loss of viable seeds. To address the presence of denser contaminants like stones and clumps of soil, the cleaned seeds are then routed through destoners. Destoners operate on the principle of density separation, utilizing airflow and vibration to differentiate between heavier impurities and the lighter sunflower seeds. As the mixture is fed onto an inclined vibrating deck, air is blown through the material from below. The heavier stones resist the upward airflow and migrate to the higher end of the deck, where they are discharged, while the lighter seeds are carried by the vibration to the lower end for collection. This process effectively ensures that only clean seeds advance to the next stage of processing. After the comprehensive cleaning process, the sunflower seeds are ready for dehulling, also known as shelling. Sunflower seeds are encased in hard outer shells or hulls that constitute a significant portion of the seed's total weight. These hulls are low in oil content and can impede the extraction process if not removed. Therefore, dehulling is a crucial step aimed at increasing the efficiency of oil extraction and improving the quality of the resulting oil. The dehulling process begins with the conditioning of the seeds to facilitate the separation of the hulls from the kernels. Conditioning typically involves adjusting the moisture content of the seeds through controlled heating or humidification. Properly conditioned seeds have hulls that are more brittle and easier to crack, enhancing the effectiveness of the dehulling equipment. Once conditioned, the seeds are fed into dehulling machines, which employ mechanical forces to crack the hulls. One common type of dehuller is the centrifugal sheller, which uses a rotating impeller to hurl the seeds against a hard surface, causing the hulls to fracture upon impact. Another method involves the use of roller mills, where seeds pass between counter-rotating rollers that exert compressive and shear forces, breaking the hulls without damaging the kernels. The choice of dehulling equipment depends on factors such as seed variety, desired throughput, and specific plant configurations. Following the cracking of the hulls, the mixture of kernels and shell fragments undergoes a separation process to isolate the oil-rich kernels. This separation is typically achieved through a combination of aspiration and screening techniques. Aspiration involves the use of air streams to lift and remove the lighter hull fragments from the heavier kernels. The mixture is fed into an aspirator, where a controlled airflow lifts the less dense hulls away from the denser kernels, effectively segregating the two components. Screening may also be employed, utilizing vibrating screens with specific mesh sizes to further refine the separation based on particle size and shape. The efficiency of the dehulling and separation processes is paramount, as incomplete removal of hulls can lead to increased fiber content in the oil, affecting its clarity and stability. Moreover, residual hulls in the meal byproduct can diminish its nutritional value and marketability as animal feed. Therefore, processors often implement multiple passes through dehulling and separation equipment to achieve optimal results, balancing the trade-offs between processing time, energy consumption, and product quality. With the sunflower kernels now isolated and free from their hulls, they are ready to undergo further processing to extract the valuable oil contained within. The next stages involve mechanical pressing and/or solvent extraction, each with its own set of procedures and equipment designed to maximize oil yield and quality. These processes will be explored in detail in the subsequent sections, delving into the intricacies of transforming cleaned and dehulled sunflower seeds into the refined oil that reaches consumers worldwide. Now it's time to go into the core phase of sunflower oil manufacturing, the oil extraction process. This is where the golden liquid locked inside the sunflower kernels is separated and collected. The extraction phase typically uses one of two methods, or more commonly, a combination of both, for optimal oil recovery: mechanical pressing and solvent extraction. Each method has its own benefits and limitations, and modern sunflower oil factories are designed to seamlessly integrate these systems into a continuous, high-efficiency process that minimizes waste and maximizes yield. The first step in oil extraction is mechanical pressing, often referred to as expelling. In this process, the dehulled and cleaned sunflower kernels are conveyed into a series of screw presses, also known as oil expellers. These heavy-duty machines consist of a cylindrical barrel housing a rotating helical screw shaft. As the kernels are fed into the expeller from one end, the screw shaft compresses them with increasing pressure as they travel along the barrel. The space between the screw and the barrel gradually narrows, intensifying the pressure and causing the oil to be forced out through small perforations or slits in the barrel wall. This process is incredibly robust and continuous, with some industrial presses capable of handling several tons of seed per hour. However, mechanical pressing alone can only extract about 85% to 90% of the total oil content from sunflower seeds. The remaining 10% to 15% stays trapped in the pressed cake, a solid, fibrous byproduct that still contains a considerable amount of valuable oil. To retrieve this remaining oil and improve overall efficiency, factories employ solvent extraction. Before the solvent extraction phase begins, the pressed cake from the mechanical expeller must be properly prepared. This involves breaking the compacted cake into smaller, uniform pieces using a cake breaker or flaking mill. The flakes are then conveyed to a conditioning unit where they are heated to a specific temperature, usually between 60 to 80 degrees Celsius. This heating not only helps to soften the cell structure of the material, but also enhances the effectiveness of the solvent by improving oil solubility and fluidity. Once conditioned, the sunflower cake is fed into a continuous extractor, typically a horizontal rotary extractor or a loop extractor. In this large stainless steel apparatus, the cake is soaked with a food-grade solvent, most commonly hexane, which has an exceptional ability to dissolve oils. The cake moves slowly through the extractor on a perforated conveyor belt or through a series of baskets, while the solvent is sprayed from above and recirculated from below. As the hexane seeps through the material, it dissolves the residual oil, forming a solution known as micellar. This micellar, containing both oil and solvent, is then pumped out of the extractor and sent to a series of distillation units where the solvent is evaporated and recovered, leaving behind the crude sunflower oil. The evaporation process is conducted under vacuum and controlled heating conditions to ensure complete solvent recovery without degrading the oil. Simultaneously, the now oil-depleted cake, referred to as spent meal, is conveyed to a dissolventizing toaster. This equipment uses steam and indirect heat to remove any residual hexane from the meal, making it safe for use as high-protein animal feed. Next, let's look at the processing of crude sunflower oil, which, at this stage, is a deep amber liquid that contains several impurities, including free fatty acids, phospholipids, pigments, waxes, and trace metals. Though technically oil, this unrefined product is not yet suitable for cooking or bottling. It must be purified and stabilized through a multi-step refining process, which includes degumming, neutralization, bleaching, dewaxing, and deodorization. The first of these refining steps is degumming. In this phase, the crude oil is mixed with a small amount of water or a weak acid, such as citric or phosphoric acid. This causes the naturally occurring phospholipids, also known as gums, to become hydrated and coagulate into a heavier phase that can be separated through centrifugation. The removal of these gums is crucial because they can contribute to off flavors, reduce shelf life, and interfere with further refining stages. The centrifuges used here operate at extremely high speeds, up to 5,000 revolutions per minute, creating centrifugal forces strong enough to separate even microscopic droplets and particles. Once degummed, the oil is subjected to neutralization, where it is treated with a caustic soda solution to remove free fatty acids. These acids can contribute to rancidity and reduce the oil's stability, so their removal is vital for producing a high-quality, shelf-stable product. The soda reacts with the free fatty acids to form soap stock, which is then separated from the oil via another round of centrifugation. The soap stock may be further processed into industrial byproducts such as lubricants or fatty acid distillates, ensuring minimal waste. Now it's time for the bleaching phase. Despite its name, this stage does not involve any chlorine or harsh chemicals. Instead, the oil is mixed with an adsorbent clay material, often activated bleaching earth or acid-activated bentonite that binds with pigments, trace metals, and other unwanted compounds. The mixture is then heated under vacuum and passed through a filtration system where the spent clay is removed, leaving behind a visibly lighter oil. The objective of this step is not only to improve the color, but also to remove pro-oxidants and residual contaminants that could impact the oil's flavor or stability. But up next is one of the most temperature-sensitive and critical steps: dewaxing. Sunflower oil naturally contains waxes that, while harmless, can cause cloudiness or sedimentation when the oil is refrigerated or stored at low temperatures. To ensure crystal clear oil, particularly for use in transparent bottles, the dewaxing process is implemented. The oil is cooled gradually in a crystallization tank to allow waxes to solidify, and then pass through chilling filters or plate and frame filter presses. The solidified waxes are captured by the filter media and removed, leaving the oil with improved cold stability and clarity. Finally, the last refining step is deodorization. This process removes volatile compounds, including aldehydes and ketones, that can impart undesirable flavors and odors to the oil. Deodorization is carried out in a high vacuum, high temperature distillation column where the oil is subjected to steam distillation at temperatures between 180 to 240 degrees Celsius. The high temperature causes the volatile substances to evaporate, and the vacuum ensures they are swiftly removed from the system. Modern deodorization systems include structured packing and multiple stripping trays that allow for efficient steam-oil contact with minimal thermal degradation of the oil. The end product of this exhaustive refining sequence is a brilliant, light yellow, odorless oil with a neutral flavor and excellent oxidative stability, qualities that make it ideal for cooking, frying, baking, and use in processed foods. The refined sunflower oil is now ready for bottling or bulk packaging, depending on its intended application, whether destined for supermarket shelves or as an ingredient in snack foods, margarine, or ready-to-eat meals. The oil's journey from seed to bottle is far from over. Now it's time to explore the next critical phase in the industrial sunflower oil production process, the packaging and distribution stage. After undergoing extensive cleaning, pressing, solvent extraction, and refining, the sunflower oil is now fully processed, brilliant in clarity, neutral in flavor, and stable for both cooking and long-term storage. But before it can reach consumers or be used by food manufacturers, the oil must pass through highly automated and carefully controlled packaging systems. These systems are designed to maintain product integrity, optimize shelf life, and meet regulatory and commercial requirements for both retail and industrial distribution. Once the refined sunflower oil leaves the deodorizer, it is pumped into large stainless steel holding tanks. These tanks are equipped with inert gas blanketing systems, typically using nitrogen, to prevent oxidative degradation of the oil. Even trace amounts of oxygen can initiate rancidity, so maintaining a low oxygen environment in storage is critical. The tanks are also thermally insulated and often jacketed for temperature control, maintaining the oil at a stable range of around 25 to 30 degrees Celsius. This ensures that the oil remains fluid and clear, preventing cloudiness that could otherwise form during cooler storage conditions. From these storage tanks, the oil is directed via stainless steel pipelines to the packaging area. The transfer lines are equipped with positive displacement pumps and high sensitivity flow meters to ensure precise, consistent delivery volumes. Before entering the filling systems, the oil passes through final filtration units, often made up of multi-layer stainless steel mesh or polymer filter cartridges to capture any microscopic particulates that may have entered during tank storage. This guarantees that only the cleanest, crystal clear oil reaches the packaging stage. The packaging line is often separated into two main tracks, one for retail-sized bottles, typically ranging from 500 milliliters to 5 liters, and another for bulk containers, such as 20-liter jerry cans, 200-liter drums, or 1 0.000 litre intermediate bulk containers for industrial clients. The retail packaging line begins with empty bottles being loaded onto a conveyor, either manually or through robotic depalletizers. These bottles are usually made from food-grade PET and are blow molded on-site or sourced from specialized suppliers. Before filling, every bottle passes through a bottle rinser, where a jet of filtered, compressed air or ozonated water is sprayed inside to remove any dust or particles. This ensures microbiological and particulate cleanliness before the oil is introduced. The cleaned bottles are then transferred to multi-head volumetric or gravimetric filling machines. These high-speed machines, capable of filling up to several hundred bottles per minute, are calibrated to extreme accuracy, ensuring every bottle contains the precise labeled volume, no more, no less. The filled bottles are immediately capped by rotary capping machines, which place and tighten tamper-evident screw caps or snap-fit closures. Some systems integrate induction sealing, where a foil liner inside the cap is sealed to the bottle mouth using electromagnetic energy. This creates an airtight, tamper-proof barrier that preserves freshness and prevents leakage during transit. After capping, bottles pass through labelers that apply pressure-sensitive or shrink-sleeve labels. These labels are printed with brand information, nutritional facts, batch codes, and expiration dates using high-speed inkjet or laser coders, allowing for complete traceability of every unit. Following labeling, bottles proceed through automated inspection systems equipped with cameras and sensors that verify fill levels, cap integrity, label alignment, and code legibility. Any non-compliant bottles are automatically rejected via pneumatic arms into separate bins for rework. Approved bottles continue along the line to automated cartoning and case packing stations, where robotic arms place them into cardboard cartons, followed by case sealing with hot melt glue or tape. For bulk packaging, a separate line handles large volume containers. These containers are positioned under filling nozzles that are often suspended from load cells to ensure accurate weight-based filling. Bulk fillers must also incorporate anti-foaming and venting mechanisms to prevent air entrapment, especially at high flow rates. Once filled, containers are sealed with heavy-duty caps or tamper-evident seals and palletized for shipping. All packaging configurations, whether for retail or industrial use, are assigned unique identifiers linked to the master production batch and logged in the plant's ERP system. Now it's time to delve into the logistics and distribution chain, which plays an equally crucial role in maintaining the sunflower oil's quality and ensuring timely delivery to global markets. Once the packaged oil is palletized, it is moved via autonomous guided vehicles or forklifts to climate-controlled storage warehouses. These warehouses are designed for high throughput and efficient inventory turnover. Pallets are organized using barcoded location systems, and warehouse management software ensures that the oldest batches are shipped out first, following the FIFO principle. Transportation from the factory to distribution centers, wholesalers, retailers, or export terminals is typically conducted in temperature-regulated trucks or intermodal containers. For export shipments, ISO tank containers or food-grade flexer tanks are used to transport sunflower oil in bulk volumes over long distances, often across continents. These tanks are insulated and equipped with inert gas blanketing systems to maintain oil stability during the journey. For local or regional deliveries, finished product pallets are shrink-wrapped, strapped, and loaded into trucks equipped with GPS tracking and real-time temperature monitoring. Each shipment includes digital delivery documents with QR codes or RFID tags that sync with customer inventory systems, facilitating seamless unloading and tracking upon arrival. Delivery confirmation, quality checks, and real-time feedback mechanisms are used to verify that every order arrives in optimal condition, both physically and chemically. But up next is one of the most critical dimensions of the modern sunflower oil industry: quality assurance and regulatory compliance. The food-grade nature of edible oil necessitates adherence to stringent quality standards at every stage of the process, from seed selection to final bottling. Every batch of sunflower oil is subjected to a comprehensive suite of analytical tests conducted in on-site laboratories or accredited third-party labs. These tests include parameters like free fatty acid levels, peroxide value, aniseidine value, color, moisture content, and soap residue, all of which provide a comprehensive snapshot of oil quality and stability. Gas chromatography is used to profile fatty acid composition, ensuring the oil meets the standard range for linoleic and oleic acid contents. Spectrophotometers analyze color and clarity, while Karl-Fischer titration determines residual moisture. These tests not only guarantee regulatory compliance with international standards like Codex Alimentarius, the European Union Food Safety Directives, and the US FDA guidelines, but also help refine internal production protocols. If any parameter falls outside the accepted range, the affected batch is isolated and either reprocessed or discarded. Up next, we focus on one of the more overlooked yet incredibly vital components of sunflower oil production: byproduct utilization and factory process integration. Modern industrial sunflower oil facilities are designed not only to produce refined oil efficiently, but also to capitalize on every possible output from the sunflower seed itself. This means that even materials which, in earlier generations of oil production, may have been considered waste, are now valuable raw materials for secondary industries or reprocessed within the factory. One of the most important of these byproducts is the sunflower meal or cake that remains after the oil has been extracted. This dense, protein-rich substance is collected immediately following the dissolventizing process and cooled using air blast or counterflow cooling systems to bring the temperature down from over 100 degrees Celsius to ambient levels. This temperature drop is necessary to preserve protein quality and prevent mold growth during storage. The cooled meal is then ground into a uniform particle size using hammer mills or roller mills and passed through vibrating screens to remove any oversized clumps. Sunflower meal is widely used in the livestock and poultry industries as a valuable feed ingredient due to its high protein content and favorable amino acid profile. Factories that produce sunflower oil at scale often have integrated bagging or bulk loading systems for the meal, allowing it to be packaged into 25 or 50 kilogram bags or loaded into bulk silos for shipment in trucks and rail cars. Some facilities even have in-house pelletizing systems that compress the meal into pellets, which are easier to handle, store, and transport. Another byproduct generated during processing is the husk or hull removed during the dehulling stage. These hulls, although devoid of oil and low in protein, have significant value as a biomass fuel. Many sunflower oil factories have transitioned to using these hulls as a renewable energy source to generate heat or steam for use in the facility. The hulls are fed into biomass boilers equipped with particulate filters and emissions control systems where they are combusted cleanly and efficiently. The steam produced powers heat exchangers for oil refining processes like bleaching, deodorization, and dewaxing, reducing reliance on fossil fuels and lowering the factory's carbon footprint. In more advanced facilities, excess steam from the coal-fired boilers is also used to drive small steam turbines, generating on-site electricity that supports lighting, automation systems, and auxiliary equipment. This form of cogeneration enhances energy efficiency and contributes to the plant's sustainability targets. Some operations even sell surplus energy back to the local grid, turning what was once a waste product into a revenue stream. Water recycling is another critical area of integration. Given the extensive use of water in processes such as conditioning, steam generation, equipment washing, and degumming, a closed-loop water treatment system is essential. Wastewater from the plant is collected in large settling tanks, where solids are removed via sedimentation. The water then passes through biological treatment units and membrane filtration systems, such as reverse osmosis or ultrafiltration, to remove organic matter, oil residues, and chemical impurities. The treated water is reused in non-critical applications like boiler feed or equipment cleaning, drastically reducing freshwater consumption. Now turning to process automation, modern sunflower oil facilities operate as highly digitized environments where real-time data governs every aspect of production. Centralized control rooms equipped with HMI panels and SCADA systems provide operators with full visibility and control over temperature, pressure, flow rate, and other parameters at each processing step. Every sensor in the system, from tank-level monitors to flow meters and load cells, is networked to a control system that not only logs data for traceability, but also actively regulates inputs to maintain optimal efficiency. For example, if a temperature deviation is detected in a deodorization column, the SCADA system can automatically adjust the steam valve opening percentage to correct the temperature within seconds. Similarly, in the filling line, digital vision systems detect the fill level and reject any bottles that fall outside preset tolerances. This integration between mechanical systems and digital controls ensures the factory runs continuously with minimal human intervention, reducing errors and improving consistency. Predictive maintenance is another application of advanced automation in sunflower oil production. Vibration sensors, thermographic cameras, and acoustic monitors are placed on motors, gearboxes, pumps, and bearings to detect wear patterns long before failure occurs. The data is fed into AI-driven platforms that analyze trends and forecast the optimal time for maintenance. This prevents unplanned downtime, increases equipment lifespan, and maintains uninterrupted production flow. Inventory management and logistics are similarly digitized. Raw materials, finished oil, packaging supplies, and maintenance components are tracked using barcodes or RFID tags that interface with the plant's ERP system. This allows real-time monitoring of stock levels, automatic reordering when thresholds are reached, and optimized production scheduling based on available resources and demand forecasts. Finished goods are tracked through the entire supply chain, and shipping documents are generated automatically, reducing paperwork and human error.